Again, thanks for the warm introduction. So what I want to do is see how I can go back. Okay, so before I get started, so let me quickly get a sense for the audience here and the level of machine learning that people know here. So what I'm going to do is I'm going to send a link to the chat window so that if try to answer. Uh, Yeah, I hope I pasted it in the chat box. So please, I mean, if someone is using a mobile or even a laptop, please. And one question that I want to ask all of you is the following. So there will be a choose the correct answer question. With four options, which I'm going to activate now. I just wanted to get a sense for uh, where people are in this group. So you can go to that link and click A, C, and D, depending on your expertise in machine learning. So if you have no prior knowledge, click A. If you have some basic knowledge, click B. If you have some intermediate knowledge, click C. And if you have advanced knowledge, please click D. Meantime, let me set it up. It will be very useful if all of you respond soon so that I can set. Yeah. And I also would like to request participants who are not speaking to be on mute so that it's not interrupt others. Okay, so for another second. Okay, so most of you seem to be people without their knowledge, which is good. So this is going to be a very, very high level introductory talk. So there are some people who have some basic knowledge, some people like 6% of you who seem to have some intermediate knowledge, not many with advanced knowledge, at least from what I see so far, which is good. So we'll wait for another 10 seconds to see if these numbers change drastically, otherwise we'll.
Yes, sir.
Okay, great. So I get a kind of a sense of where people are. So that's good. So I'll tune my presentation accordingly. Okay, so let's get started. Maybe I'll stop this. Thanks everyone for responding. So let's get started. I hope you're able to see my screen.
Yes, sir. It's visible, sir.
Okay, great. So yeah, so participants, feel free to stop me at any point. Do not wait till the end to get your doubts cleared. So we'll talk as we go along, and if you have any questions, stop me and we'll get it answered. Okay, so okay, so let's get started. So this is going to be a yeah. Okay, so this is going to be an intro to machine learning kind of a talk. So as the introduction was, so my name is Arun Rajkumar. I'm an assistant professor in the Department of Computer Science and Engineering at IIT. I completed my PhD from Indian Institute of Science, and my broad interests are in machine learning, statistical learning, theory, and ranking. And today we are going to talk about machine learning at a very, very introductory level. So what does it mean? So what are the core subjectives or the stock subjectives? So we want to understand what are the key paradigms of learning from data. So we'll try to understand what it means to first say learning from data is, and then we'll see what are the different paradigms of learning from data. And we'll talk about a few popular algorithms for machine learning in each of these paradigms that we'll talk about. And we'll hopefully understand, I mean, I'll kind of indicate the different applications of machine learning where these algorithms that we see will actually be used. So this is the overall idea of the next, let's say, 45 minutes to an hour. So why should you even care about machine learning, right? So that is the first question. You are here, all of you are here for a certain reason, which means all of you are aware of why you should care about machine learning. But then let me give you my thoughts. So this is so on the left, what you see is the Google Trends. Uh, 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 Google Trends for the keyword machine learning. What I mean is basically the number of people or the volume of people searching for the term machine learning over the past few years, right from 2004 till today. As you can see that the number has kind of peaked up significantly in the last few years, which means more and more companies which are data rich are trying to use machine learning techniques to make their algorithms or make their products better naturally. And so there is a heavy need for people who know machine learning, right? So that's why you should care about this, and not just that. So I think one of the very popular magazine called Forbes Technology Council magazine lists top 10 trends in the next 10 years. Here are the top 10 trends. There are some in black and some in purple. And the ones in purple are like around half of the top 10 trends, which include chatbots, driverless cars, automation, machine learning, deep learning, voice control, and so on. And all of these use some kind of machine learning or that. So in some sense, these are all things that depend on data and making sense of data. Right, so it means that out of the top 10 trends, if 5 trends are extremely dependent on machine learning, it is better that we equip ourselves with this emerging field. Right, so that's the goal of this talk. So why should one care about learning? Right, so what does it mean to learn from data, and what can you do if you learn something from data? Right, the first thing that you can do is what is called as prediction. What does this mean? This means that I have some data, I have learned something, and then tomorrow if somebody comes and asks, let's say this is a bank, and bank has a lot of historical data with which it is doing some kind of a learning, and tomorrow you go and ask the bank, hey, can you give me a loan? And then it's going to give you an yes or no answer, right? So on this, so is there a question, Divya? Can you unmute and ask a question if there is one? Sorry. Anyway, okay. So maybe that was a mistake. Yeah. So if a bank has the bank is trying to do some kind of a prediction whether you should be given a loan or not, right? So that is a prediction problem, and this is something that you can learn from data to do well on questions of prediction. What else can you do with data? What you can do is, in general, what is called as recognizing insights or patterns, right? So, for instance, in the picture here. So again, this is from some source which I have listed here in gray. Probably it's not very clear, but I'll make it clear when I share the slides. But yeah, so let's say the picture at the top is just a picture of the road that a driverless car is actually looking at, and it has to make sense of this picture, right? So it needs to know where are the cars, where is the road, where are the trees, and where is the the divider, and so on, right? So nobody is, it kind of has to do it automatically. And in this case, a list of things that it might want to figure out is, let's say, sky, building, pole, road, pavement, tree, sign, symbol, fence, vehicle, pedestrian, bike, right? So each of these are important things for it to make some decisions as to how to navigate the road, right? So and this is what is called as mining or gaining insights about patterns just by looking at some data. This is also an important subfield of sub question that machine learning tries to answer. And the third one, which we'll briefly look at today, is what is called as learning a sequence of decisions, right? So what does this mean? Let's say you and your friend are playing chess. So you play a move, and then your friend plays a move, and then this game keeps going on between both of you. Now, if you replace your friend with the machine has to make a sequence of decisions, and you are responding to the machine's decision by making your own moves as white. Let's say the machine is playing black. Now, every time it plays a game, it's going to be a different moves that the opponent is going to play, and it has to learn well to play over a sequence of decisions, right? So there's a thing that there is a component of time here, so that decisions are taken over time, and then you want to make better and better decisions with the goal, of course, to win the game, right? So so data in this case is not like available in one shot, but then it comes over time, and then you still keep adjusting to the situation. So this is also what we will call as learning from data. I'll make all these more precise as we go along, but these are the kind of the high level goal. So let me also make it clear what do I mean by what do I not mean by learning from data, so that we are absolutely clear as to where we are in terms of understanding what does it mean by the term learning. So this is what I mean. This is what I don't mean when I say learning from data. Let's say calculating the income tax, right? So how do you calculate income tax? You have some income, you have certain set of rules, and if you fall in one of the income brackets, you'll have to apply one of these rules, and then at the end of the output of this applying these rules is the amount of tax that you have to pay to the government, right? So there is no learning happening here because it is a simple rule-based algorithm that takes as input your income and then outputs, let's say, income tax. Of course, it can take more things as input. Your input, your income, your let's say savings and your FDs and RDs and whatnot, and then what it outputs is simply a number, which is the amount of income tax that you need to pay, right? So there is nothing about predicting anything, or there are no insights to be gained, or there is no sequence of decisions happening, right? So in that sense, this is simply what we will. This is something that we will not call as learning, right? So this is a rule-based algorithm, which is something different from learning. Whenever I say learning, it is, of course, it's going to be an algorithm, but then the algorithm is going to critically depend on data. And when we see some examples of this algorithm, it will become much more clear. And the second key important distinguishing factor between what is learning and what is not learning is this concept of memorizing, right? So let's say you are in a school environment, let's say an academic environment. So your teacher comes and teaches you let's say the 5 tables, right? 5 ones are 5, 5 twos are 10, 5 threes are 15, and so on, till let's say 5 20s are 100. This is what you are taught in class. Now, in your exam, if you are still going to be asked one of these questions, right? So either 5 into 1 is what, or 5 into 10 is what, or up to 5 into 20, right? So if you are only going to be asked questions from this set, then so there is one strategy to do really well in this exam, which is simply to memorize all the answers. You don't really have to understand how 5's table works. You just have to memorize that if the input is 5 and 2, then my output is going to be 10. My input is 5 and 7, my output is going to be 35. Right? So there is no real understanding happening of the 5's table itself, but then you are simply mugging up things, so to say. Right? So, and that is what we'll call as memorizing, and which is not what we want to say when we say we want to learn from data. Because when you say we want to learn from data, it means that you not only want to do well in the data that you are given provided, but also you want to do well in data that you have never seen before. For example, in the 5's table question, so let's say if you are asked a question in the exam which is 5 times 25, but then you have only studied till 5 times 20, and if you have memorized, you are going to fail. On the other hand, if you have really understood what does it mean to say what a 5's table is, you'll be able to what we call as generalize to unseen data, and this is a very, very key factor in good learning. So it should not simply memorize, but you should be able to generalize. Okay, so we will go into some some paradigms of machine learning, but I'm going to quickly stop for a second and ask if there are any questions at this point so far. So anybody who has a question can unmute, otherwise you can mute your mic. Is there any question so far? Okay, great. So it has been kind of
no, sir, very clear, sir. No, very clear.
Okay, great. So let me go ahead. So now what we want to do is look at a specific paradigm of machine learning, which is called as supervised learning. I'm sure you might have heard this term in the previous talk, but let me also, for completion, make it clear what it is, and then talk about some algorithms. So what do I mean by supervised learning? So what is the setting here? So here is the problem, right? So given the loan history of customers, you want to predict if a new customer will pay back the loan or not, right? So this is a very important problem for a bank, because it's going to sanction loans, and it has to be very sure that if I sanction, let's say, 1 crore to a customer, and then if he or she runs away with the money, then I'm at a loss, right? So I must have some confidence that the customer is going to pay back money, right? So, but how do I build this confidence if I have not seen this customer? It's the first time somebody walks into my bank. I have to still make a decision whether I have to give this person a loan or not, right? So now the only thing that can guide us is the history of how previous customers have performed, right? So every customer so far in your history of your bank, let's say for 30 years, you have provided a loan, and then the customer has either defaulted or has paid back, right? So this information you have. Now somehow you have to use this information to make a decision of whether to give a loan to a customer or not, whom you have never seen before. This is what we'll call as the first problem, which is a supervised learning problem. So let's, for example, take this customer whom we'll call as Ashok. And now Ashok comes in, and you have past customer history, and then you put all this details into a box, which we'll call as the machine learning box, and out comes the answer whether it is yes or no. Right. So now the question is, what happens inside this box? This is the box that we will care about in this talk. We'll try to understand this. Right. So the way we will understand this is, what do I mean by past customer history? So it means there are two main features, two main pieces of information that I have about the past customers. The first piece is what we will call as features, and the second piece is what we will call as label, right? So in this case, in this particular example, the features could be as follows. So I have the name, I have age, I have gender, education, salary, married, location. These are all things that I know about my previous customers. Let's say there was a customer John who was 29 years old, male, etc., etc. Now, when this particular customer John when he was given a loan, did he return it back or not? In this case, yes, right? So he did return it back. So he was a good customer. On the other hand, if you look at a customer Smith, who was 36-year-old, who was got a BS education, had a salary $4,500, he did not return the loan, right? So this is all the information that you have with you. Now here comes Ashok. Right, now you have to make a decision for him. The first thing you need to do is collect some features for Ashok, right? So what is your age? What is his gender, education, salary, and so on. And now the only thing that you don't know is, well, the label for Ashok, right? So whether will he return pay back the loan or not? This is what we need to find out. So which means, to make the previous box much more clearer, what we want to say is, you have a feature for the new customer Ashok, which you feed into this box. And you also have the feature label pairs of all the customers' historical data. And using this information, you somehow have to make a decision, yes or no. Right? So now this is what we'll call as learning from data. Right? So you are somehow using the past data to make a prediction on a new person whom you have never seen before. Right? So the algorithm itself is going to be data driven. We haven't seen what the algorithm is going to be. We'll see a couple of algorithms, but at this point, think of this as a black box, which is going to be a data driven black box, which is going to make its decision based on this data. Right? Now, we are going to call this kind of setup as a supervised learning problem. Right? So it's a learning problem all right, because it takes data and makes decisions. Hence, it's a learning problem. Now, what does this word supervised mean? The word supervised means that for every person in your history, you have some supervision, whether the person returned the loan back or not. So you have labels for every feature that you have. And this label information is what we'll call as supervision. So somebody is supervising, telling you that, hey, if these are the features, this is the answer. These are the features, this is the answer. These are the features, this is the answer. Now here is a new feature, give me the answer. Right? So because you have this label information, we'll call this a supervised learning. Okay, so that's just a name for this type of, this is a paradigm in machine learning. Okay, so now, now the question is, let's get into the black box and try to develop some simple algorithms for this problem and see what would be a good algorithm, right? So anybody, can you tell me what is a good algorithm for this problem? How would you go about solving this, even before we see the algorithms? Anybody who has not seen machine learning before, can you think of how you would try to solve this problem? Anyone? It's okay if the answer is wrong. There is no right or wrong answer. Try to come up with something. What do you mean? So how do you think about this problem? Right. So let's say you are the bank. You have this information, and now you have to make this decision for a show. How would you make this decision? Anyone?
Yeah, hello sir. Yeah, here I think age factor and salary package will matter, and he's not married. So based on that algorithm, I think bank sets.
Yeah. So in this case, would you give the loan to Ashok or not?
Yes,
Okay.
because he's very young age and having good package.
Yeah. So his young age. So the intuition is that he's young, he has money, he's not married, so probably doesn't have much dependency. So he'll probably give back. So that is how you would analyze if you are. That is how the mind is trying to analyze. Right. So now we want to. The computer cannot make these inferences as how the human is doing. So, but then we want it to be an algorithm, right? So we cannot like when you have hundreds of customers coming in, and then you cannot go into details for each of these customers and try to get this. So you would want to do it in an automatic fashion. Let's see how we can do that, right? So the first algorithm that we are going to see is what is called as KNN. I'll try to explain the meaning of the name KNN as we go along, but let's first look at the algorithm. For this case, as somebody mentioned, it looks like the age and salary are some kind of important things here. So for the sake of simplicity, I'm going to restrict my problem as to having only two features, which is the age and salary. This is simply for explaining to you in an easy way, graphically. But in a general machine learning problem, you will have many features. But let's for the moment concentrate on only two features, which is age and salary. Right? Now, so how does this algorithm work? Basically, what it's going to do is going to do as follows. So it's going to think of each of these features. Age is a feature, salary is a feature. It's going to think each of these features as one axis, right? So this is the age axis, and here is the salary axis. Okay, and now each person is now going to become a point. Can I request the person who is talking to mute himself? Yeah. So there is a age axis, there is a salary axis, and each person becomes a point in the space. For example, if you look at John, he's 29 years old and he has salary some $12,500, whatever it is. On the other hand, Smith, who is older but has less salary, falls somewhere here. Mary is younger but has more salary, falls somewhere here, and here is Ashok. Now, from this picture, if you have to make a decision, right? So now we are saying we are going to look at this algorithm, this data in a graphical fashion, which is what I have plotted here. Now, from this picture, do you think Ashok should be given the loan or not? If so, how are you making this decision? Anyone? So here is the new guy, Ashok, and we have to make a decision for Ashok. Mary, John, the green ones are people who have been given the loan. The red guy is the one who has not been given the loan before. Now here is the new guy. How will you make a decision for the new guy? He should be provided with loan. Kajol says, why? Why do you think so? What made you say? You are right, but why? What is the intuition? On the graph created, maybe you should unmute and talk. It's easier. Positive side. Yeah. What is a positive side? I didn't understand that. So what is a positive and negative side? Yeah. As it falls under the threshold.
Hello, Arun, am I audible?
Yes, you are audible. Go ahead.
Yeah, like I was saying that since the graph that has been created here, the John falls beside the line of the Ashok. So like he's between the Maddie and Ashok field. So maybe like yeah, he should be provided with the loan. That's what I was saying.
Okay, okay. So I think I get the question of whatever you're saying. All your intuitions are correct, but let's try to make it more formal and precise in terms of an algorithm because we want the computer to do this, right? So one way to do this is false, right? So you're simply going to decide whether you're going to give the loan to Ashok or not based on his neighbors. When I say neighbors, it means that not friendship relation, but then nearness, closeness relation in this picture, right? So Ashok is here. Now, if I only have to decide based on who is the closest guy to Ashok, right? So I don't have Ashok in my database, but then who is the closest person to Ashok in my database? In this case, who would that be? That would be John. He's really close to Ashok. So was not given a loan or not? Yes. So I will decide Ashok also to loan. Let's see, right? So this is my algorithm, right? So I don't have this person in my database, so I look at the closest person, and if that person is given the loan, then I will sanction this loan. So is this a good algorithm, or is there any issue with this? Anybody? Krish Kumar Sharma, are you speaking? I'm not able to hear you. Okay, so can someone think of whether finding the nearest neighbor and then giving loan based on his or her decision, is that a good idea or a bad idea? Is there any possible pitfalls of this? It's a good idea. People say it's a good idea. Well, fine. So it's a reasonable idea, definitely. But what you may want to do is, so let's say you have by mistake in your history, right? So this John, who was a good person in some sense, who had a good salary, but then whose age was also less. But for some reason, he was denied a loan, let's say, right? Which was a wrong decision. Or maybe your data was wrongly entered in your database. That John's answer was no. So then, sorry. Then if you go by just the neighbor, you might make a wrong decision. So to make your algorithm a little bit robust to errors like these, what you could do is, instead of looking at just a single neighbor, you can look at multiple neighbors. In this case, let's say you look at k neighbors, and then you take the majority of these neighbors, right? So in this case, let's say if I take two neighbors, in this case, John and Mary would be the two neighbors, and then I take the majority decision, right? So in this case, both of them were given the loan, so the majority would also be given the loan. So I can give Ashok the loan. So if I make 2 as 3, still the majority will be, my neighbors will be Mary, John, and Smith also, the 3 nearest neighbors. But then 2 of them were given loans, whereas Smith was not given, right? So in this case, just to make the algorithm a little bit more robust, what we do is we don't just look at single neighbor, but then we look at k nearest neighbors, right? So on this algorithm is what is called as simply KNN. For k is the number of neighbors you are looking at, and NN simply means nearest neighbors, right? So this is one of the simplest algorithm that you can have to learn from data, right? So this is the first thing that anybody can think of while learning from data. But this algorithm, if this was this algorithm is very simple, but if it's really good, then probably we won't need any other algorithms in machine learning, right? So we would be done with the talk. Unfortunately, there are some issues with this algorithm. Let's look at some of the issues. So before I look at the issues, are there any questions about the algorithm itself? Is the algorithm clear? Any questions? Okay, so if you have any questions, just ask me as we go along. So for now, I'm assuming you've understood the algorithm. So there are a couple of issues with this algorithm. I'm going to state 3 of them. the first thing is, well, how do you choose k, right? So you have to make a decision as to how many neighbors am I going to consider to make a decision. Is it going to be one neighbor, three neighbors, five neighbors, seven neighbors? I don't know, right? So I need to make this decision as to choose k. The second thing is, how am I going to measure distances between features, right? So one feature here is age, one feature is salary, right? So is it even proper to uh, kind of measure distance when these features are so different from each other, are not probably in the same scale and so on? So that is another problem to keep in mind. The last thing, which is perhaps the most important disadvantage of this algorithm, is that for every new person that you have to have the data of everybody in your data set, right? So everybody in your data set, uh, in your historical data set, plays a role in the decision. You may think that it's only the k nearest neighbors who play a role, which is correct. But then to find these k nearest neighbors, you have to first find the distance to everybody in your data set, sort them, and then take the top few, right? So, and if you have, let's say, 1 million people in your database, and for every new person, you have to do huge amount of computation. In this case, you have to find 1 million distances and then sort them and then take the top few and so on. And new guy comes, you'll have to repeat the whole thing again, right? Which means, well, you have not, in some sense, really learned from the data, but then you have not learned a good representation of the data, so to say. But then the whole data is necessary to make a decision for a new point. And that is something that we will try to avoid in the next algorithms that we will have. Right? So these are three major issues why this algorithm is not always used in practice, but it's a reasonable algorithm to start with. So now we'll go ahead and see a different algorithm for this problem. Right? The second algorithm we'll talk about is what is called as a decision tree algorithm. So what does this algorithm do? Well, this algorithm is going to do the following. Again, you start with this data. So in this case, I have 4 points in my historical data, and I still want to predict my answer for this new show. So the way I'm going to do this is, I'm going to convert this data set into a tree. When I say tree, it's a computer science binary tree. We'll see what it is in a minute. Once I have converted this into a tree, I don't any longer need this data set. I can throw all the data points away, and I will only retain the tree with me. For instance, if I had 1 million data points, I will convert this 1 million data points into a succinct small tree and then throw away the points. The points are no longer relevant to make my predictions for the new point. So what is this tree that you will build from this data set? So here is a tree, right? So let's say this is the data set that I had, and then I'm converting it into a tree like this. The first question, so the tree has some some ellipses and some rectangles. In every ellipse, you ask a question, which is something of the form, is some feature less than some value, right? So that would be the question. If the question is yes or no, depending on that, you move either to the left of the tree or right of the tree, right? So in this case, the question is, let's say age is less than 30, and in your, based on this data set, what we'll decide is anybody who is less than 30, right? So anybody who is greater than 30, in this case, there is only Smith, and he was not given a loan, right? So we'll decide the moment the age is greater than 30, I will say no. But then if the age is less than 30, then there are 3 people with age less than 30, John, Mary, and Susan, of which John and Mary were given the loans, but then Susan was not. Now, how do I decide when the age is less than 30? I look at salary. If the salary is greater than, let's say, 10,000, then I will say the loan can be given. Otherwise, the loan should not. Right. So now, if I can convert my data set into a tree like this, then for Ashok, can you tell me for Ashok if the loan will be given or not based on this tree? Anyone? So how would you predict Ashok's answer can be given? Why do you think Venkatesh or Shrish, why do you think Ashok should be given the loan? He will be given, yes. Why? Because you start with age, you check if age is less than 30, yes. Is the salary greater than 16,000? Yes. So he should be given the loan, right? Now the question is, so we have said that, well, if I have this tree, I'll be able to decide how whether to give the loan to Ashok or not. The more important question is, how do I decide? How do I come up with this tree given this data? Right. So that is the more important question now, right? So we need to somehow find a method to convert this data into this tree. And the way, I'm not going to really explain in detail how that happens, but basically what you do is you take every feature and you look at every threshold and see how does it divide your set of people, right? So let's say in this case, if I take age and 30, it divides my data set into two parts, where in the left part there are 3 people, on the right part there is only 1 person, and the right part is kind of a pure part, right? So whoever is on the right part, which is Smith, was not given the loan, which means everybody in the right part was not given the loan. On the other hand, on the left part, there were 3 people, out of which 2 people were given the loan, which means the purity of that left part is somehow like 2/3. Now you want to do this in an iterative fashion so that you get as pure parts as possible, right? So for instance, if I had instead said, let's say age is less than, let's say 25, in this case, so then what would have happened? So then Susan would have fallen on the left side, whereas everybody else would have fallen on the right side, right? Susan would have been given a loan, would not have been given a loan, which means that Susan would have been pure. On the right side, again 2/3 of pure. So that is also a reasonable way to fix a age less than value here. On the other hand, so if I had age less than 28, let's say in this node, then what would have happened? 2 people would have fallen on the right side, John and Smith, whereas Mary and Susan would have fallen on the left side. But then both the left side and the right side nodes are impure, right? So both have both yes and no answers. And that's not a good way to split this. So you'll have to find the right way to split it so that the nodes on the left and right side become more and more pure. Right? So this is the high level intuition. We won't go into the mathematical details of how exactly this is done, but this is the high level intuition. The algorithm itself, if I have to summarize, simply does the following. You find some most informative feature, threshold, in this case age, 30, let's say. Now split data according to the feature, and then you recurse, right? So you again go into the left side, right side, and then do the same thing. Find the most informative feature and recurse, and keep doing this, right? So this is the high level algorithm, and this algorithm is what we will call as a decision tree algorithm, for the simple reason that we are deciding based on a tree, and that tree is called as a decision tree. So any questions about this algorithm? No questions?
I think it's clear as of now, sir.
Okay, great. So let me move on. So again, there are some common issues with this. One main issue that nearest neighbor had was the fact that you had to store all data points, but we have removed that issue here because we can throw away the data points and only retain the tree. But now other issues crop up, which is more than issues. It's like a design choice, I would say. One of the questions that you need to decide is, how deep should I go in this tree, right? So maybe in this tree, I could have simply stopped at, if the age is less than 30, give the loan. If its age is greater than 30, don't give the loan, right? So that is also a valid decision tree, right? So now I decided to go one step further and do this. Now you could go one more step further if necessary in other data sets and so on. So where do you stop, right? So how do you stop the depth of the tree? That's a very common question that one needs to answer before even running this algorithm. The other thing is, how do I decide what it means to say some feature is informative, right? So there are multiple ways to decide this. We won't really discuss in detail about this, but there are these things called Gini index, information gain, and so on. Different ways to decide what should come where in this tree. So that is something, again, as a design choice, as a designer of a machine learning algorithm, you should have it. But this is the high level idea, right? Okay. So now let's move ahead to slightly complicated algorithms. So this algorithm, so requires some amount of understanding of probabilities. So if you understand probabilities, you will probably follow whatever I'm going to say in the next 5-10 minutes. If not, I'll try to give you a broad overview of what this algorithm is about, and then you can go back and read more. Right. So the algorithm is what is called as a naive Bayes algorithm. Bayes is one of the greatest early mathematicians. Is Thomas Bayes. It's named after him, and it makes a very simple and a naive assumption, and hence it's called as a naive Bayes. I will talk about what this assumption is as we go along. Now, so one way to model machine learning algorithms is to decide how this data in my history, right? So the historical data that I have, how did it get generated, right? So I want to make some assumptions as to how this data itself was generated, right? So that is what is called as a generative modeling of data. And this naive Bayes algorithm makes a certain assumption as to how this historical data itself was generated in the first place. And that is a probabilistic assumption. So here is the assumption. Now, to create one new entry in my database, let's say John 29, 12,500, yes, right? So let's say this is one data point that if I have to add this, this was, let's say, not there in my database, and now I have to add a new data point in my database. Now, the way I am going to generate this is the following. I'm going to toss a coin, and if the coin falls heads, I will decide, well, I'm going to generate a person for whom the loan will be given. If the coin falls tails, I will decide I'm going to generate a person for whom the loan will not be given. This is what I'll call as a class. Class is yes or no, whether the loan will be given or not. I'll first toss a coin. Let's say the coin fell heads. Now I'm going to generate the features corresponding to the guy for whom the loan will be given. Now, how will I generate that? So in this case, I have two features. Now I'm going to generate the salary according to certain distribution, and I'm going to generate the age according to a different distribution. Think of this as, let's say age is between 1 and 40. Now I'm going to roll a die, and this die has not 6 faces like the usual die, but it has 40 faces, let's say. Right? So I will roll this die. Whichever face it falls in, I'm going to say that is the answer for this person's age. Similarly, I'll pick one for the salary as well. Right? So I'm going to call. So now what are these distributions? What do I mean by these distributions? So when I say I'm going to, let's first look at this picking the class yes with probability C. When I say pick class yes with probability C, it means that I'm going to toss a coin, and this coin is not a usual coin that we have in our pockets, which comes heads or tails with same probability. But then this coin has some weight on one side, which means maybe it is more probable to come either heads or tails. We don't know, but it's a weighted coin, and that weight is somehow indicated by the C. Let's say if the C was, let's say, 0.9, then the chance that it will fall heads is much more higher than the chance that it will fall tails. Right? So similarly, the die that I will roll will not fall equally likely between numbers between 1 to 40, but then some numbers are more likely than some other numbers. Same for salary. Right? So let's somehow abstract this by saying that the class will be picked with probability C, the salary will be with some distribution S1, age with some distribution A1. This is if the coin fell heads. Now if I toss the coin, if it fell tails, now I'm going to generate a data point with class no, right? So where the loan will not be given. Now for the no guy, the salary is going to be from a different distribution, right? Because we saw that the guys with yes will have salaries around greater than 10,000, which means the weight of the die that you're rolling will have more weight on values greater than 10,000. Whereas for the no guy, the salaries with weight less than 10,000 will have more weight. The die's value with less than 10,000 will have more weight. Right? So that is called as S2. Let's call it S2, and age with some other distribution A2. Right? So now remember, this is not true, right? So this is not how loans are generated, how people's salaries and ages are generated. But I'm going to assume that this is how the data was generated. My data was generated. Now the only thing that I have to learn is what are these parameter values? C, S1, A1, S2, A2. These things I have to learn, right? So for the moment, the way you learn these parameters from data is what is called as an estimation problem, right? So somehow you are given this data set and you know that you are making an assumption that each point in your data set is generated according to certain model. Now you want to, and these models have some parameters, in this case C, S1, A1, S2 and A2. Now given this data, I want to estimate this parameter, the best parameter values that will explain my data. Now we won't really go into the details of how to do this estimation. Let's say now I somehow convert this data set into simply these values, C, S1, A1, S2 and A2. Right? So this is how I think the data is generated. Okay. Now what do I do with these values? Now I want to do something called as inference, which is given a new data point, in this case Ashok, with salary age 28 and salary 16,000. I want to calculate the probability of giving this person a loan using what is called as a Base Theorem, right? So I hope most of you must have seen Base Theorem, right? So if somebody has seen Base Theorem before, can you just type yes? I just want to get a feel for people have seen this theorem. Anyone? If you remember what this theorem is from your probability classes, if you have some intuition about probability. Okay, so some people know the Bayes theorem. Good. Okay, so what is the theorem? The theorem is the following, right? So P of A given B is simply, you can write it in terms of P of B given A, P of A by P of B, right? So in this case, we are going to use the Bayes theorem for something very specific. We are going to find, so given this new guy Ashok, what are we interested in? We are interested in the probability that the decision for Ashok should be yes or no, right? We want to find the probability that the decision for Ashok is yes, given that Ashok's age is 28 and salary is 16,000. This is what we want to find out. Now, how will we do that? We'll use the Bayes theorem to say that P of A given B comma C is proportional to P of B comma C given A into P of A. This is what the Bayes theorem is, right? So which means to decide Ashok's probability of being given a loan, I should understand first, among those people who were given the loan, what is the probability that that person had age 28 and salary 16,000, similar to that of Ashok, right? And how many people were given the loan? These two things will matter. Now, if you know these two values, you can find out the value for whether Ashok should be given the loan or not. This is the Bayes theorem's relation. Now, so basically, we need to understand these two products, right? The project probability of age, comma salary given yes, probability of yes. Now, how would you go about doing this? Now, this is, we have used the Bayes theorem. Now, we have to make the naive assumption, which is kind of saying that probability of age 28 and the salary is 16,000 can be written as probability of age 28 given yes times probability of salary 16,000 given yes. You are kind of writing this joint distribution, probability of A comma B given C as probability of A comma A given C into probability of B given C, which you cannot do in general, right? So it is not true in general, but in this case, we are going to make that assumption. And then we are simply going to say, now the decision of yes given age is 28 and salary 16,000 depends only on three things. The probability that among those yes people, what is the probability that somebody had age 28? Among those who are given loans, what is the probability that somebody has salary 16,000? And how many people among all that people, what fraction of people were given the loan? And these values you can get using your values here, right? So probability of age given yes is simply this value A1, right? So whenever there was an yes, the probability of an age is modeled using this S1, A1. And whenever there was an yes, the probability of salary is modeled using this S1. And whenever there is a yes or no is based on this value C, right? So now you can basically, the high level idea is you estimate these probabilities using data. And now using this and using Bayes theorem, you somehow make a decision for a new data point. I know it's if you're seeing it for the first time, this might be slightly might look complicated. But the main idea is that you are converting your whole data set into a bunch of probability distributions, and you're using these distributions to make decisions for new people whom you have not seen. Right? So this will give you a probability that the loan should be given to Ashok or not. And if the probability is greater than, let's say, 0.5, then you give the loan, otherwise you don't give it. This is the algorithm. Any questions about this algorithm? Okay. So we can discuss more about this algorithm as we go along if necessary. But let me. Yeah. Okay, so there are a few other algorithms which are interesting algorithms. I'm just going to give you some high-level view of some popular algorithms in machine learning. One of the very popular algorithms is what is called as a support vector machine algorithm. I won't really have the time to explain why it is called support vector machine, but I will at least give you some idea as to what the algorithm does in a pictorial way, right? So let's say we try to plot the points of everybody in our data set, people who were given loan and people who were not given loan, right? And the data look like the following, right? So in the picture that you are seeing, the green people were given loan and the red people were not given loan, let's say, right? So now you have to somehow throw away the data points, but then retain only the most important information from this data, so that you can make new decisions for new people who come later. How would you do that? One way to do that is, let's say I think of it looks like I can separate the red from the green by drawing a line like this, a brown line like this, which means for anybody who is coming new, I will simply say if he falls on the left of the brown line, I will say he should not be given loan. On the right of the brown line, I will say he should be given loan. Now, is this a good line that separates this data? What do you think? What do you guys think? Is this a good line that separates this data? Or is there some other better line that separates the red from the green? Anyone? So how many of you think this is a good line? If you think this is the best line that you can think of that separates red from green, just say yes. Okay, good. Somebody says no. Dr. Pungodai. So anybody else thinks no, or everybody else agrees that if you are given these red and green points, line can start from origin. Okay. So somehow that's this. So this doesn't seem to be that great a line. Is that the sense that I'm getting from all of you? Okay. So I'll give you one more line. You can tell me whether you like the brown line or the new line that I'm going to give. Let's say we look at this line, the yellow line. So now, which one do you think is a better line that separates the red from the green? Is this the brown line or the yellow line? Just type it in chat. I mean, brown or yellow? Yellow. Okay. Most people think it's yellow, maybe. Okay, good. Most people think it's the yellow line. Great. Why? What is so special about yellow line that is not there in brown line? What is the intuition? What is so special about yellow line that everybody seems to think yellow is better than brown? Anybody? I mean, what is the intuition, right? So all of you say some answer, but I just want to hear your thoughts as to why that would be the answer that you're thinking. Space is equal, half division. So these are the kind of intuition that data is divided in equal parts. Somehow you're saying, well, even in the brown case, it is divided into equal parts, right? So there are equal number of red and green parts. So there is some other sense of equality or space is divided well that is coming into mind. So let's again, the whole idea of machine learning is to formalize this intuition into rigorous algorithm. So one way to do this is to look at the following, right? So of course everybody thinks yellow is better because the distance to the closest point from yellow, right? So this is how I am separating these guys. The distance of this line to the closest point on the red and closest point on the green side, right, is higher than what you would have gotten had you used the brown line, right? So the distance to the closest point to the brown line is really close. Now, why is that not a good idea? Because so let's say I had a point. If Ashok, let's say, fell in the place where I am showing the cursor. So are you able to see my cursor? I hope you are, right?
So it's visible, sir.
Okay, great, thanks. So let's say I have a point that falls here now, which is very, very close to this brown line, but on the other side, right? So a brown line would say this is on the green side, the loan should be granted. Whereas maybe the loan should not be granted because it's much more closer to the red points in some sense, right? So in some sense, if you slightly get a noisy data, right? So slight deviation from this, it is not robust enough, the brown line, whereas the yellow line seems to be much more robust. And this is the intuition that all of you had, that it has to somehow divide it into equally and so on. This way of doing things is what is called as a margin. This distance between the closest points on either side of the yellow line. And the algorithm that what is called as a support vector machine is the following. So you want to somehow maximize the margin among all possible lines. You look at every single line in the space, that every line divides the space into two parts, and among all possible such lines, for every line you will have some kind of a margin, right? And you want to find that line which has the maximum margin. But at the same time, you also want the fact that the red guys are on one side and the green guys are on the other side, right? So you don't want a line to wrongly classify the red and the green. The line should separate the red and the green. Among all those guys, all those lines which separate the red from the green, you want to find that line which has the highest margin, right? So, and this algorithm is a very reasonable algorithm to start with. Just that it has one small problem. Let's say in real world data, you'll always end up with things like, okay, maybe I should add that before going to the problem, let me simply add that for a test point, you will classify it based on which side of the line the point falls on, right? So once you have gotten this line, you can throw away this data. The data is no longer necessary for me. I'll only retain this line. And now for a new point, I will simply say which side of the line it falls on, and then that would be my answer, right? So that is clear. So now one problem with this approach is that in real world data, it is often not so well separated, right? So the red and the green will always not be so well separated. It might so happen that there is one small red on this side and one green in this side. Maybe this is a data entry mistake, right? Somebody entered the data incorrectly, and you had some big issues because of that. Now what happens? No line can separate the red from the green. Now, if you try to find the answer to the one that maximizes the margin, well, there is no answer simply because there is no line that separates the red from the green at all in the first place. So then this algorithm is kind of useless, simply because there were two guys who were outliers, and that kind of screwed up the entire algorithm, and we don't want that to happen. And for that, the way we will handle that is by doing something very interesting. I'll try to again explain this in an intuitive fashion as well. So instead of solving the top problem, we will solve what is called as the bottom problem, which is by saying that, well, I don't mind if they are outliers. Now I'm going to find a line such that if the point, so if a green point falls on the left side of this line, then it has to pay some penalty, and that penalty is how much should it pay to get to the other side of the line, to the right side of the line, right? So in this point, the green point has to pay this amount. Think of this as some kind of a money that this green point has to pay so that it comes to the correct side of the line. None of the red points have to pay anything because they are on the correct side of the line already. None of these green points have to pay anything because they are also on the correct side. Now, this red point has to pay something to go to the other side. Now, you want to find a line such that the amount that each of these data points pay is as small as possible, right? So you want to maximize the margin. At the same time, you want to minimize the amount that each of these data points pay, right? So if in the previous case, none of the data points would have paid anything, that is the minimum amount that these data points can pay. Everybody pays 0 because there were clearly separating a line that separates the red from the green. On the other hand, if there is no line, then I will pick a line for which the data points will pay the least amount. So I want to minimize the amount that the data points pay. At the same time, I want to maximize the margin also, right? So maximizing something is same as minimizing the inverse of it. So I will put these two things somehow together as I want to minimize. Think of this as the inverse of the margin plus some penalty that each of the data point is going to pay to go to the correct side. Of course, once it pays this, then you want the fact that the classes red and class green are on the opposite sides of the line when moved a distance depending on the penalty. After paying this penalty, everything should look all right. So now this is the new problem that we will solve, and this way of looking at this problem seems to be extremely useful in practice, and this is a very fundamental algorithm that has performed extremely well in practice. Okay, and this algorithm is what is called as a support vector machine algorithm. Yeah, so one of the things that immediately will come to mind is that, well, this is a great algorithm, all right, which takes care of outliers also. But what if there is no line that separates my data itself in the original, not outliers, but then the data itself has some structure such that there is no line that separates the data? What does that mean? Let's say we take a data set like this, right? So you have green points, you have red points. Now there is no line that separates the green from the red points, but I cannot say that there are some outliers here, right? So it is not outliers. There is some inherent structure in the data, but then the structure is such that I cannot separate it using lines, right? So now what do I do with this? Can I still use my support vector machine, which is what I'll call as the SVM algorithm? SVM stands for support vector machine. Can I somehow use this again in this setup also? It turns out there is a nice way to do this. I'm just going to give you a high-level view of how to do this. The way you do this as follows, right? So you are in 2 dimension. You have 2 features, let's age and salary. You somehow artificially make this a 3-dimensional feature, right? So you somehow think of this as not 2-dimension, but 3-dimensional feature. We won't get into the details of how exactly this is done. But then once you move from 2-dimension to 3-dimension, suddenly what happens is that you can divide these two things using a plane. Like in 2-dimension, it's a line. In 3-dimension, it will be a plane, right? So while it is not possible to divide the green from the red in 2-dimension using a line, it is possible to divide the green from the red in 3 dimensions using a plane. So now what you do basically is that you push your data points from low dimension to high dimension, and then you kind of divide it using a plane, right? So that is the basic idea of support vector machines. Maybe what I am going to do is, okay, I have another few minutes, right? So I have another 4-5 minutes for this session.
Yes, sir. Yes, sir. Please carry on.
Yeah, so I'll complete a part of this and then we can probably stop.
Sure, sir. Sure, sir.
Yeah. Okay, so this is what the SVM algorithm is, and it works very well in practice, even if your data has this non-linear relationship between your features. And this is very common in real world. You might not always have a line that separates the positives from negatives, from the people who are given loans versus people who are not given loans. I mean, you might have something else, and in this case, this algorithm still works. So there is another class of algorithms which is very popular. I mean, it's gaining much more popularity these days, and I think some of the future sessions of this course might talk about much more about this algorithm. So I won't really talk much, but I'll give you some hint as to what this algorithm is. It's what is called as a neural network based algorithm. So what it does is that, so it takes as input your features, right? So your height, your age, your salary, your whatever other details that you had. Let's say if you have 3 features, you will have 3 inputs. Now, what happens is So you have one line that's, I mean, you somehow combine these inputs in different ways, right? So you somehow probably can combine these as age plus 2 times salary plus 3 times some other feature. Third feature is one hidden value, and you can combine it in different ways, multiple different ways, and somehow think of it as taking a kind of a majority vote, or somehow combining these combined features also to give an output, right? So you have some features, you have some aggregated value of these features, which is what we'll call as these hidden input nodes. And once you have these aggregated features, you somehow combine these you use these aggregated features to get the probability of output for each of these data points. So what does that mean? So that means that so instead of learning, think of this as this way. Instead of learning one line that separates the data, maybe in this case I cannot learn one line, but maybe I can learn multiple lines, and then I can take each line will tell me whether to give a loan or not, and then I am somehow taking the majority of these lines and making a decision based on that, right? So, and in that majority classifier, majority algorithm might actually work well. Now think of each of these hidden units as finding one line which will say yes or no, and now this output is somehow using all these yes or no's from each of these lines, combining them into some probability whether the decision should be yes or no, right? So think of this as some kind of a weighted majority, right? So 5 people are saying yes, 3 people are saying no, 3 lines are saying no. Then you would if you go with the majority, then you would say the answer is yes. On the other hand, maybe each of these lines themselves have some weights attached to it, and now you want to do a weighted majority, right? So you'll multiply the answer using its weight of how important this line is, and then you will do a weighted majority. If the weighted majority is, let's say, greater than 0.5, then you will say the output is yes, otherwise you will say the output is no. Now, how do we come up with which are the lines which I should learn from my data, and what is the right way to combine these lines into a probability? So that is what this algorithm does. It automatically tries to learn these weights and this way of combining these lines into probabilities, and this is what is called as a neural network. Now this can be extended to multiple layers. You can learn lines, and then you can learn lines over the answers given by these lines and answers given by these lines of lines and so on, and you can keep going as much as you want. So in essence, what is happening is you are taking your input. Instead of learning a line, you are learning some complicated shape in your space that divides your green points from the red points, right? So in this case, this shape might be like very complicated like this, right? So the way I'm tracing my thing, so it might be some non-linear complicated curve, and to learn this non-linear function is the goal of this what is called as a neural network. It's basically learning a non-linear function which, for given a new input, will say whether the output is yes or no, right? So that is what the high-level goal of what neural networks is. Of course, these days, I'm sure multiple other people will talk about this. People talk about what is called as deep learning, which is like a revolution in machine learning. If you don't understand what I'm saying, I'm going to say now, don't worry, I'm sure multiple people will talk about this in the workshop. So basically, you have, instead of age and salary as features, now here the input itself is like a picture, right? So in this case, it's a car. And you want to decide whether the input is a car or a truck or a van or a bicycle or what it is, right? So this is the problem. Right, so given an image, you want to decide what is the object category in the image. Now, how do we, in terms of age and salary, these were numbers, and it was easy to play around with these numbers. But then if it's an image, how do you convert this image into numbers? You can think of some pixel values. And now what this convolutional neural network does is, it's again neural network. Instead of learning lines and so on, it's what it learns what are called as filters, right? So it will kind of first try to detect edges in this picture, and if the edges are of some way, then it kind of combines these edges into some high level things. So maybe in this layer it will only each of these is called as a layer, and in the first layer maybe it will only find edges in layers as we go along, it will find maybe some headlights, maybe it will find some tires, and then if the object has 4 tires and 2 headlights, then it will decide whether it is a car or not, right? So this is a much more complicated algorithm, but then because it comes from the input is not simple numbers, but then images, and it's more specialized to this. And whenever you are encountering what is called as deep learning, I'm sure you will understand this in much more, right? So maybe what I think is I'll stop here, take a break, and then we'll come back and cover the second part of this talk, if that is okay.
Yes, sir. So I think we'll break for now. We'll break for about 10 minutes, and
Sure.
then we'll once again assemble. The link will remain the same.
Sure.
So we can once again log in.
Yeah, so you can do that. I'm going to be around, so if you have any questions, you can ask me in the break.
Yeah, maybe participants who would like to clarify meanwhile while the class is dormant, so you can use this time.
Yes, definitely. Thanks. It's a non-linear function. Linear means line. Non-linear means anything that is not a line is a non-linear. Think of it like simple, right? For instance, if you think of parabolas, if you know parabolas and let's say a sine curve, right? So in this example, you kind of maybe it's a sine curve happening here, right? So it is not really a sine curve, but then it's like a much complicated curve, not a line. That's what I mean by non-line, line-ish functions. Any other questions? Okay, so okay, there's a question about Gini index. Right. Can you see my screen?
Yes, sir. It's visible, sir.
Okay, great. All this. Okay, where is Gini index? Okay, so without it's basically a formula. I'm not really going to write down the formula because I'll have to explain a lot of other things if I have to do that. So on the other hand, what I want to do is I'll kind of give you an intuition as to how to come up with this, right? So think of it as a measure of purity of a feature comma threshold choice, right? So in this case, let's say there are two options that I could have used. Either age is less than 30 or age is less than 20. These are two options I could have used. So in this case, if I do forget the rest of the tree, right? So you are starting with the root of the tree. Let's say age is less than 30. So in this case, what happens is there are 3 people who fall on the left side, John, Mary, and Susan, whereas only one person falls on the right side, which is Smith. Now think of these as 2 sets of people along with their labels, right? So on the right side, only Smith is there and his label is no. On the left side, there are 3 people, 2 with yes and 1 with no, right? So now you want to somehow say, if I make this particular choice of dividing this whole data set based on age less than 30, then how pure are my 2 sub trees, right? So let's say how to compute this pureness. the way you will compute this pureness is what is the, so on the right side I only have Smith, only one person, and he was not there are 0 yeses and 1 no, so that's a very very pure node, right? So because everybody on the right, when I say pure, everybody on the right side has the same decision, whereas on the left side not everybody has the same decision. 2/3 of people have yes decision, 1/3 of people have no decision, correct? So this is on the left hand side. So now Gini index is somehow using these numbers 2 by 3, 1 by 3 on the left side, and 0, 1 on the right side. What is 0, 1? 0 means 0 people have decision yes, 1 is 100% fraction of the people have decision no, right? So now somehow combine these into a single number using something called as an entropy, which we won't really I won't really write it down here, but think of it as somehow combining this into a single number such that the closer they are to 0 and 1, the higher the value is. The highest value you can get is when both sides become pure, right? So let's say for the moment there was no Susan in this data set. There were only 3 people, John, Mary, and Smith, and now I divide based on age less than 30. Right? So the right side is of course Smith with 36, and he's a pure node. On the left side, is it pure or not pure? What do you think? If I divide based on age less than 30 and there are only 3 people in my data set, John, Mary, and Smith, what happened to the left subtree? Is it a pure tree or an impure tree? Anybody? Vidyashri? Hope you're around. So the question is clear, right? So if I put age less than 30, and let's forget Susan and Ashok. Let's say we only have John, Mary, and Smith. If I say age less than 30, then who all will fall on the left side? Can you type it on the chat so that I know that you are following? John and Mary, correct, thanks. So John and Mary, and both of them were, the decision is yes, right? So which means 100% of the people were given the loan, 0% were not given. That's what I mean by a pure node. The right side is simply Smith, who is also a pure node, because 100% people on the right side were also given loan and we are not given, right? So now this is a pure split, which means my data set can be divided into people who are given loans and people who are not given loans simply by using age less than 30. If there was no Susan, both sides will be pure. Now, if there is Susan, then no matter which age and age value I choose, there is always going to be an impurity. Now, let's say I take 2 different options and see which is more impure, right? So let's say I take age is less than 30, which means my right side is going to be simply Smith. Now I'm looking at all 4 people. Now my right side is simply going to be Smith, which is a pure guy, pure side. But the left side will have 2 people yes and 1 people no, 1 person no. John and Mary will be yes, but Susan will be a no, because all of them had age less than 30. So that is an impure thing, right? Only 2/3 of the, it's only 2/3 pure, so to say, right? On the other hand, if I choose age less than 28, let's say, now what happens to the right hand side? How pure is the right hand side if I take age less than 28? What percentage pure is the right hand side? Anybody? Age less than 28 is the question, and what 50%, right? So that is correct. Why 50%? Because when you say look at age less than 28, on the right hand side is all people who have age greater than 28, which is John and Smith. But then John was given loan, Smith was not given loan, which means it's only 50% pure. Now what about the left side? How pure is the left side for age less than 28? what percentage of purity is there on the left side? For age less than 28. Anyone? 50% again, right? Simple. So if age less than 28, then the remaining guys are all with age less than 28. In this case, Mary and Susan. But Mary was given the loan, Susan was not given the loan. But the left side is also 50% pure, right? So now you can choose whether to split at age less than 30, which will give you right side is completely pure, left side is 66% pure. On the other hand, if you do age less than 28, right side is also only 50% pure, left side is also only 50% pure, which means which is a better split? You want to become as pure as possible as you go down. Is age less than 28 better or age less than 30 better? 30 better, right? So simple, right? So now I mean, now how do you, Gini index is one way to combine these four numbers, the purity numbers, into a single number such that the more the pure the split is, the higher the value is. Right? So that's all it is. I hope that is clear. Any other questions? Oh. Yeah, feel free to ask questions. More questions you ask, more you learn. I'm sure you're seeing it, especially for the first time, you should have a lot of questions. Yeah. Funnel trick? Okay. Yeah. Okay. How do I say that? Okay. So basically, so if you have data which can be separated by a line, then you can set up a problem like this, and then you can get a line which separates the red from the green. Life is simple, easy in this world. On the other hand, if you have data which cannot be separated by a line, then what can you do is the question, right? So what is essentially happening is that well, so when you say that, okay, so it takes some time to understand. I mean, it will take some time to understand, but then realize that when you say there is a line that separates, let's say I mean, this is age, let's say this is salary, and then this is a line. What it means is that there is a linear relationship in some sense between the age and the salary, right? So anybody on, yeah, so okay, so let's not get into the mathematics, but anybody on the left side of the line is positive, and anybody on the right side, I mean negative, and anybody on the right side is positive. Now, because that cannot be done here, simply because there is no linear relationship between these features, age and salary. But there may be some non-linear relationship. Maybe if I plot instead of age and salary, maybe if I plot, let's say, age square, salary square, age into salary, something like that, right? So each axis is no longer my original feature, but then some new features that I'm thinking of, right? So let's say this new feature can be some complicated combination of these original features. In this case, let's say it is age squared, salary squared, and let's say age into salary. There are three different features. I've converted my two features into three features, and I'm again plotting my data in this three-dimensional space as opposed to two-dimensional space. And in some cases, maybe in cases like this, it could so happen that if I choose to measure different features like this, then there is a nice separation in this higher dimensional space where I can simply divide this data green from the red using a plane. Anybody on above the plane is positive, anybody below the plane is negative, right? So this essentially what it means is that this complicated line here, curved line here, will correspond to this plane in the higher dimensional space. That's all it means, right? So which means if I think of different new features in higher dimensional space, then I get a linear relationship. When I say linear, in higher dimension, line means plane. Right? So in 3D, a line is just a plane. So anybody on one side of the plane is a positive guy, other side of the plane is a negative guy. Right? So these are the guys who should be given loan, these are the guys who should not be given. While it was not tough to find it using a line here, with these new features, it becomes easy. Now, there are several questions that should come to your mind. Well, how do I decide what these new features are and how many such features should be there and what is this kernel, name kernel, and so on. So that would need a complete explanation of this algorithm, which I don't want to do due to lack of time. I mean, the idea is the crux of the idea is that you can get these new features. Okay, let me look at the question. There's a question. So this plane will have some orientation on both axes, meaning how do you decide that the point from where separated this? So are you asking Vivek, how would you decide whether
Yes, sir.
the point falls on the top of the plane or the bottom of the plane? How do you decide? Is that the question?
Right. So means in between that, some threshold is there, or what? How to set this plane, or is this imaginary, or what?
No, it's not imaginary. Okay, so this algorithm is going to tell you what this plane is. Right? So this algorithm, so instead of maximizing our lines, the margin, now so this line was only in 2 dimensions. Now you can go to 3 dimension and do the same algorithm, right? So let's say in 3 dimension, my data was like this. Now I want to, again, I can draw 2 different planes, right? So one plane which is very close to the greens and one plane that is equally distant from green and the red. And I can ask the same question like I asked for the line, which one you prefer? And of course, all of you are going to tell me that you will prefer the plane which will equally kind of separate the green from the red. And that thing is again can be formalized in the same way as a margin, right? So instead of maximizing over lines, now we will maximize over all planes the margin such that the class red and green on opposite side of the plane as opposed to the line. That's all it is, right? So the mathematics of how do you get it is an entirely different thing, right? So we'll have to write down equations and solve the problem and so on, which we won't do now. But then all I'm saying is that think of an equivalent of line in high dimension as a plane, and this algorithm will find the plane for you. Is that clear?
Okay, sir. Understood. Thank you.
So I think it's now time to resume our session, sir. You can go ahead with your
great
session.
So what I am going to do now is so I have some more stuff left from this talk itself, which I will talk about, and towards the end of this talk, maybe last half an hour or so, I will talk about online learning. I think it is important that people understand the machine learning basics well before we go into advanced things. Is that reasonable?
Certainly, sir. Yes, sir.
Okay, great. So let me do. So we were here. So basically so far we have seen several algorithms, right? Starting from nearest neighbors to decision trees to naive Bayes to support vector machines to neural networks to convolutional neural networks. There are a host of algorithms that you can do for supervised learning. But in general, are there any way to say these algorithms fall in one class versus the other, right? So are there different classes of these algorithms? Indeed, there are. So there are 2 different types of modeling that is possible. One is called as what is called as a generative model, and the other is what is called as a discriminative model, right? So let's first look at what a generative model is. A generative model, for what a discriminative model is, and then we'll come to this generative model. A discriminative model is something that is trying to discriminate the yes from the no directly, right? So it is trying to directly attack the problem of modeling the probability of the label given the feature, right? So what is the label? Label is your decision for the loan, yes or no. Feature is your age and salary, and you want to directly find for a new guy what is the probability that the loan will be given that the feature is age is so much and the salary is so much. You directly want an answer to this question, and that is what is called as a discriminative modeling. Why is it called discriminative? It tries to discriminate between these two labels, yes label and the no label directly, and hence it's called as a discriminative model. It directly maps from feature to label. You are just trying to understand a function from feature to label. What's this function in the case of SVM? It is just the function that will tell you whether you are on the right side of the line or the left side of the line. Right. So in the neural network, again, it is going to tell you somehow you are going to convert your data into some probabilities, and is this probability output greater than 0.5 for class 1 or less than 0.5 for class 1, where 1 is like, let's say, the yes. Right. So you're directly going to convert your input into these probabilities or these decisions, and that is called as discriminative modeling. On the other hand, there is other type of modeling which is called as a generative modeling, which models not just probability of label given feature, but it models something extra, which is what is called as the joint distribution of feature and label. Right. So if you know probability, you'll probably follow this. If not, it's not very critical, but then try to get a high level overview of what this is. Right. So you want to understand what's the probability of this particular feature occurring in my data with this particular label, right? So we want to understand both. Whereas in this case, in the discriminative case, you don't really care how the feature was generated. Somebody gave you the feature, and the only thing that you care about is what is the chance that the feature, for this feature that I have been given, the label is yes or no. On the other hand, here you are also trying to model how the feature itself was generated, right? So for instance, when we were discussing about naive Bayes, we did the following, right? We first tossed a coin. If the coin fell heads, then we went ahead and generated a feature for the yes class. And if the coin fell tails, we went ahead and generated a feature for the no class, right? So which is what I'll call by feature, probability of feature given the label, right? So once the label is picked by tossing some coin with probability P of label, now fixing that label, we also want to model what is the probability of the feature, right? So in some sense, we are completely trying to model how the data is generated. So in plain English, let's say the difference between these two models is as follows. Let's say we are trying to predict whether a given sentence is spoken. Let's say somebody speaks a sentence, and we want to understand if the sentence that was spoken was in let's say Tamil or not. Tamil is a language, so we want to understand if the sentence is in Tamil language or non-Tamil language. Now, I'm sure many of you are here or speak Tamil, but many of you here don't speak Tamil, right? So maybe 60% speak Tamil, 40% don't speak Tamil. I don't know the geographical distribution of this group, but let's assume that 60% speak Tamil, 40% don't speak Tamil. Now, your generative model would tell you to decide whether a sentence that was spoken is in Tamil or not. You need to completely understand how to generate sentences in Tamil. That is where the generative word comes from, right? So you are trying to model from a generative way. You want to understand how the data so let's say my data my data set had a lot of Tamil sentences and a lot of non-Tamil sentences. Now I am going to understand from the data how Tamil itself can be generated. And using that, if I predict for a new guy, whether it is Tamil or not, then it's a generative modeling process. But then you may argue that there may be many non-Tamil speaking people in this audience who still be able to figure out whether a given sentence is in Tamil or not in Tamil. Maybe they won't be able to generate new sentences in Tamil, but then they will still be able to say whether a given sentence is in the Tamil language or non-Tamil language. Let's say somebody who speaks Telugu, right? So who has no clue about how to write or speak Tamil, will probably still be able to figure out whether a sentence is in Tamil or not. He'll be able to discriminate whether the sentence is in Tamil or not Tamil, right? So given the sentence, the probability that it's in Tamil, which is the probability of label given feature, is what that person's mind has learned. It has not learned what is the way to generate Tamil languages, right? So now the question is, if our goal is only to figure out whether a given sentence is in Tamil or not, then why are we even caring to learn how to generate Tamil sentences? We will only want to discriminate between the language. I mean, whether it is Tamil or not Tamil, right? So if that's the question, that's a very good question, right? So now then we are essentially asking, should we think about generative models or discriminative models when we are trying to run some algorithms? Now the answer is there is no clear answer to this, right? So both of these are useful approaches, but the way to think about this is as follows. Well, if you can really model how to generate sentences in Tamil, you can only be better off, right? So there is nothing that is going to hurt you if you model the generative process well. But then if you don't model it properly, then you may not, it may only hurt you, right? So which means the golden rule that one should follow while coming up while trying out algorithms for machine learning is, if you have reason to believe that the data is generated in a particular fashion, then you should use that information and go for a generative model. On the other hand, if you have no idea how the data is generated, but I only care about how to discriminate the yes class from the no class, then I should not make any generative assumption. I should simply try to get a discriminative model, which is like find a line or find a non-linear line or non-linear curve or something like that. Right? So this is a subtle difference between the types of modeling. And here's the thing to keep in mind. As you see more algorithms in the next few days, ask the question to yourself whether it is a generative model or a discriminative model. Are we directly trying to find the answer given the input, or are we also trying to see how the input itself is generated? Right? So that would be a good exercise for you as you learn more and more algorithms in this course. Okay, so now we'll go ahead and see some of the possible issues with this setup, that the way that we have discussed. One of the main issues that might happen is like, so we want to understand, in the k nearest neighbor case, we kind of left it open that how do you choose how many neighbors should I compare to make a decision. I'm going to take a majority vote, but how many neighbors should I take into account? Should I ask before I make my decision? In the decision tree, we can keep adding new nodes to make the left and right nodes more and more pure, but how deep should the tree go, right? So I mean, the tree can go as deep as possible, such that every node will become pure at some point. Should you go till that level, or should you stop? Similarly, in the SVM case, let's say one of the questions that you need to ask is, how do I map from the lower dimension to the higher dimension, right? So what are the features that I should use in the higher dimension so that I hope to get a plane that separates the positives from the negatives in the higher dimension. Similarly, in the neural network case, the question could be, well, we said that we will first learn many lines and then take a combination of these lines. Now, then we said that there could be multiple layer neural networks where you will first take combination of these lines and then learn lines over lines and so on. Now, how many layers should the neural network have is another question that one may need to answer. Right, so these are parameters of these algorithms that you have to fix before you input your data to the algorithm. Right, so k, or the depth, or the kernel, or the hidden layers, and so on. So these are what are called as hyperparameters, and this needs to be tuned typically. Right, so while before running the algorithm. So now what happens is that if you don't tune them properly, two problems can happen. One is what is called as a overfitting problem. The other is what is called as an underfitting problem. Right. So let's look at the depth case in the case of decision tree to explain this. I think that's the best way to explain this. So if I simply use only my depth as 1. Let's say I only used my age, 30 as my let me just go there. Yeah. If I cut off the tree here and I simply used age less than 30, then I might actually be using a very, very reduced power model than adding more depth to this. But then what might happen as you add more and more depth is that, let's say if there are some outliers, now just because that outlier will make some right side or left side impure, you will add more features and more depths to make it much more purer and purer, right? So which means if you add lot of depths here, you are essentially trying to what is called as overfit, which means you are trying to model the outliers as well. On the other hand, if you kind of use very less number of layers, then you are essentially forgetting the fact, you are missing out the important structure in data, right? So you are using a less powerful way to classify the data than what you can actually use, right? So this is what is called as the problem of underfitting versus overfitting. Depending on if the depth is too small, then it is underfitting. If the depth is too large, then it is overfitting. Similarly, if the K is too small, it is underfitting. If the K is too large, it is overfitting. And the same for the kernel. Similar analogy holds for the kernel and other things. Now, how do we then decide what is the right K, what is the right depth, what is the right kernel, and what is the right number of hidden layers? There is no single way to do this. But in practice, I'm going to tell you what is the most popular way people used to do this, right? And that is what is called as cross-validation. What do you do here? Well, you are given some training data and you have some test data, right? So training data is all your historical data with loan given or not. Let's say there are 10,000 points here. And the unseen test data is, let's say there are 100 people standing in queue whom you have never seen before, first time walking into the bank, and you want to make some decisions for them, right? So you don't know these unseen data beforehand, right? So you can only run your algorithms on the training data. But the problem with most of our algorithms seem to be that you need some kind of parameter tuning. And how do you tune these parameters? If you don't tune them properly, your algorithms might either underfit or overfit. For that, to overcome that, what is typically done is that you don't take all your data in your data set and run the algorithm, but then you typically take only, let's say, 70% of your data and call them your training data, run your algorithm only on these 70%, and think of the rest 30% as what is called as a validation step, right? So now for this 70%, you can try different values of K, right? For instance, for the K nearest neighbor, or for the decision tree, you can try different values of depths, and each of that will give you a different tree. Now, for each of these trees, you can try it out on the validation set. Because of the validation set, which is the remaining part of the training data, you have the labels. You can be sure that you can at least find out for which value of K do I get the highest accuracy in the validation set, right? So think of this validation set as a proxy for this unseen test data. You won't show this to the algorithm. You only run your algorithm on your training data, get different models, each for different parameters, and then test it on the validation set. And whichever parameter gives you the highest accuracy on the validation set, then use that parameter, right? So either use that parameter to retrain the entire data, and then use it to make decisions for the unseen test data. This is what is called as a cross-validation procedure. Any questions about this? Okay, so if there are no questions, I'll move on. So here is the idea: train on training data, test on validation data, pick parameters like K, depth that minimizes validation error. Now, what might happen is that you might sometimes become unlucky, and all your outliers might end up in this validation set, right? So you randomly pick some percentage, 70%, and put here. The rest 30% goes here, and if you are simply unlucky that day, it might so happen that this validation set is not really representative of your training set. Lot of outliers might be here, and that might guide you to choose a wrong parameter. So what typically people do is that they divide the training data into K different parts, right? So if this k is not the same k as the k in the nearest neighbor, right? So think of this k, let's say, as 10 different parts. If you had 1000 data points, divide it into 10 parts of 100 each at random. Now test it on 9, train it using 9 parts and test it on the 10th part. Now train it again using a different 9 parts, test it on the remaining left out 10th part, right? So, and you do this in 10 different ways, right? Because in every way one piece would be left out, and you use that as your validation set. And now you kind of average out your performance on all these validation sets, and pick your parameter, which kind of minimizes the average performance in all these folds. These are called as folds. In all these ways of splitting the data. Any questions then? So this is what is called as a k-fold cross validation. Typically, it is more robust because if one validation set is bad, still if there are 10 sets, the hope is that the rest 9 will take care of finding the right parameters. Okay, good. So we'll move on. So again, few more technical terms. These are all things that you might come across if you're doing a proper machine learning course, but I'm just going to throw these terms to you, and so that you know at a high level at least what these terms are. Right? So there are two fundamental things that affect how good an algorithm is. Right? So how do you judge the performance of an algorithm? The only way to judge the performance of an algorithm is how good does it perform on unseen data. I don't care how good it performs on my training data. If all I care about is how good it performs on training data, then I can simply memorize, right? So, but we said that we should not memorize. That is not what we mean by learning. So we want to see how good our algorithms perform on test data, unseen data, right? And to determine the goodness of an algorithm, there are two key parameters for each algorithm that determines how good the algorithm is. Right, so this is what is called as a bias and what is called as a variance. So let me tell you what each of these two things is. So so essentially, let me first tell you what we require, and then I'll define these two terms. We want algorithms which have low bias and low variance. But some algorithms might have low bias, high variance. Some might have high bias, low variance, and some algorithms are hopeless in that they have high bias and high variance. Now, what do I mean by bias and variance? Right? Now, bias is what is called as a modeling error. Right? So, I am saying, if I am imagining that my data, if it is 2-dimension, I can plot and see if there is a line that separates my data. Let's say if my data is 100-dimension, then I cannot really plot and visualize if there is a line or a plane that separates my positives from the negatives. But then if I really make an assumption that, well, I think that there is a line that separates this data, now that is a modeling assumption that I'm making. Well, in my 100-dimension space, there is a line that separates my data, positives from the negatives. And I'm going to find this line. Right? So the model is that there exists a line. Now, in reality, is there a line or not? We don't know. Now, how good is my model in representing the reality or the truth is what is called as a bias, right? So, how biased is my assumption that there is a line that separates the positives from the negatives? This is what is called as a bias, right? So, for example, look at this example. Let's say my data actually was a sine curve, right? So, my x-axis and y-axis are two features, and they are related using, let's say, a sine curve with some noise. But then I think that my data is actually a line, right? So this is a major mismatch with respect to what I think my data is, but then what the data actually is, right? So which means doing this this modeling assumption suffers from high bias. If I'm trying to find a line to separate the positives from the negatives, while actually the curve that separates positives from the negatives is a sine curve, then my model suffers from a high bias problem. Now, what is variance? Variance is slightly more tricky. It kind of captures how sensitive is my model to small changes in data. Right? So let's say I have a model, and let's say I'm trying to find. Now I know that, well, my lines don't fit well, let's say instead of lines, I fit some polynomial. A polynomial may be like a 2-degree polynomial is simply a quadratic function. A 3-degree polynomial is a cubic function, and so on. Let's say I fit a 100-degree polynomial for my data, right? My data is still so my data is still generated using a sine curve with some noise. I mean, meaning it does not exactly fall on the sine curve, but up and below the sine curve somehow. Now, if I am trying to fit this data using a 100-degree polynomial, what happens is that it might fit my data exactly well, right? So my data, my 100-degree polynomial might be very complicated function, which will go through every xy point that I have. It will exactly classify the positives and negatives in my data correctly. But if I slightly change my data, right? So if I make slight changes in data and again run the algorithm, it's going to give me a completely different answer, right? So because the 100-degree polynomial will not be so stable. On the other hand, if I am thinking of a line and if I slightly change one point in my data set of 1000 data points, the line that comes out of it will not change much. So if your model changes by a lot, if you change a little bit in your data, then it is called your model has high variance. Now, the golden, the holy grail is to achieve a model with low variance and low bias. So, but typically this is very tough to get. We might typically, some models that we have might have high bias but then low variance, whereas some other models might have high variance and low bias. Unless you know something about how the data itself is generated, it's typically very hard to say, very hard to get a model with low bias and low variance. So think of this, if you did not understand this discussion exactly the details, you can simply think of this as, in some sense, bias means, a high bias means underfitting, high variance means overfitting, right? So underfitting means when the depth is, you should have actually had a depth 5 decision tree, but if you chose a depth 1 decision tree, then that's a high bias model. On the other hand, if you chose a depth 100 decision tree, that's a high variance. Right? So it's very sensitive to outliers. That's what it is. Okay. So we should be very careful about these things. Okay. So that is all I had to say about supervised learning. We'll move on to other paradigms now. But before we move on to the fundamentally different paradigm, I also want to indicate that there are other ways of thinking about supervised learning. So instead of just 2 classes, give a loan or don't give a loan, you might want to, given a text like this, you might want to determine each letter whether it is which alphabet it is, right? So in this case, whatever I have written in this is my input, and my output should be, in this case, this is R, this is E, this is M, and so on, right? So each letter can fall into not just 2 classes, yes or no, like how we did earlier, but now it can fall into one of the 26 classes, let's say, which is any of the alphabets. And this problem is what is called as a multi-class classification problem, because you have multiple output classes. The labels can be anything from A to Z. Well, in some problems where the labels could not just be multi-class, but it can be any real number. For example, if you're trying to predict how much rainfall will it happen tomorrow, based on looking at the amount of temperature, precipitation, and so on as features, and this amount of rainfall could be any positive number, right? So it can be, let's say, 183.25 centimeters or something like that. I'm just looking up a number, and so it is not like yes or no. It's also not like giving a class like A to Z, right? So there are not a fixed number, but then there are infinite possibilities for the answer, and such problems are called as what is called as a regression. There are other problems called as ranking problems, where, for instance, if you are using Netflix or Amazon Prime or something like that, and you want to kind of for every movie in their database, for you, they want to kind of predict what is the rating or ranking that you would give for this movie. Let's say, would you rank it 1 star or 2 stars or 3 stars or 4 stars or 5 stars, let's say, right? So now it can be thought of as a multiplex classification problem where there are only 5 different ratings. But the problem, but there are some subtle differences. Maybe we won't really go into the details of that here. It just at a high level, if I have to say it in one line, it simply means that in this problem, if you predict instead of r, if your algorithm predicts r as k, that's a mistake. If your algorithm predicts r as, let's say, p, that's also a mistake, right? So these two mistakes are equally worse, right? So predicting r as p or r as s doesn't matter. Both are wrong. On the other hand, in the Netflix problem, predicting a 5-star rated, if the truth is 5-star, but then if your algorithm predicts it as 4-star, that is a smaller error than predicting a 5-star rating as 1-star. That's a bigger error, right? So because there is an ordering among these labels, sometimes if you have these ordering among labels, such problems are called as not simply multi-class classification problem, but are called as what's called as an ordinal regression problem, where there is an order in your output labels. Yes, the stars, right? So Gopesh Chandra says rating stars. Think of these as 1-star, 2-star. This is what exactly, right? So you kind of press that when you watch a movie. That's what I mean. Okay, good. So we won't really talk about these things, whereas I want you to introduce you to another fundamental paradigm in machine learning, which is what is called as an unsupervised learning. Whatever we saw so far was supervised learning, where you had some features and you had some labels, and you wanted to somehow come up with an algorithm which, given a new feature, will predict the label well. So in some situations, this may not be what you want to learn from data, where the problem is you may not have these labels in the first place, right? So essentially the labels were what we called as some kind of a supervision, but it may not be always available. And in those cases, you want to still do some kind of a learning from data, and that is what we'll call as unsupervised learning. And let's see what some examples are. Right? So what is the setting here? So the setting is that you are given some bunch of data points like this, and I am not telling you anything about what these data points are. Right? So what labels do these data points are? Right? So, but if I ask you to somehow, let's say, group these data points into meaningful groups, where meaningful, whatever meaningful means to you, how would you do that? So first of all, how many groups do you think are there in this data set, and what are they? So how many groups are there in this data set? So can you guys type your answer in the chat? Okay, 3. Yeah, most of you think there are 3 groups in this data set, right? Which is correct, but nobody is going to tell you that. But let's say we try to find these 3 groups. What are these 3 groups? In this particular case, these 3 groups are simply going to be something like this. I'm sure all of you thought of these 3 as the 3 groups in the data set. So now the question is, given a data set like this, I'm not telling you any labels about this. I just want you to automatically divide this data into meaningful groups. In this case, you have to decide how many groups. Let's say somebody told you 3 groups, and then you want to divide it into 3 different groups. So now, how do we do this? How do you think we can develop an algorithm which, given this data set, will automatically output this is group 1, this is group 2, and this is group 3? How do you think this can be done? Anybody? Any suggestions? How can we go about doing this? Based on color? No, right? So there is the color is what the output was, right? So that's what I want you to understand, right? So this is the input. The input is, you don't know the color. The input is just a bunch of data points where for each data point you have the x value and y value, x value, y value, and so on. Now you somehow have to group these into 3 different groups, where each group, I'm just coloring these groups to show that these are, the algorithm has found this is the set of groups points with single group, and this is a set of points that the algorithm thinks have to be grouped together, and I've just put a color to it. This is not given as input to you. If this is given as input to you, then there is nothing, right? So I mean, there's nothing to do. This is what is given as input. Yeah, so some people say analyzing distance between points, closeness between points, which are very good answers, right? So somehow you have to see how these points are related to each other using some kind of a distance. And then, well, nearest neighbors of whom every data point has nearest neighbors. You're right that we need to somehow think of neighbors who are close by, but every point has a different neighbor, set of neighbors. Now, how do you come up with an algorithm which will automate? The input is this, the output has to be these groups. All your intuitions are correct. You need to somehow use your neighbors. You need to somehow use distance and closeness. Question is how. Let's see how to do this. There's one nice algorithm which can be used to do this. Let me describe that. And this algorithm is what is called as find points. Okay, let me take find points that are furthest and group their neighbors. That are furthest and group their neighbors. I see. Okay, so you're saying, so before doing this, let's look at this. So you're saying, Jasmita says, you take 2 points which are as well separated as possible in your data set, and then do what? Then group their neighbors. So that will divide your data set into 2 groups. But in this case, you want 3 groups, right? So how would you do 3 groups? Which means somehow the intuition says that instead of 2 furthest points, you somehow want 3 points to start with, right? So each point somehow representing each group, and then you do something based on that, right? So your intuition is correct. So let me formalize this and say, in general, if you want k groups, how would you go about doing this? And that's exactly this algorithm, what we will call as the k-means algorithm. I'll tell you why it's called this name. But before that, let's look at the algorithm first. The first step of the algorithm is what is called as a pivot step, where what you do is you simply take 3 points arbitrarily. This can be there. We'll come to this to choose this, but then for the moment, think of it as taking any 3 points. In this case, I'm taking these 3 points. I'm going to think of each of these points as coming from a different group. We'll call a group a cluster. Let's call this the yellow cluster. This is the pivot for the brown cluster, and this is the pivot for the green cluster. Now the question is, the other guys are all gray, right? So I don't know their colors. Now I have to assign a color to each of the other guys. So how can I assign a color to each of the other guys? If I know this is yellow, this is brown, and this is green, how do you think we should assign the color to each of the other guys? What's the easiest way to assign colors? For instance, what color should this guy be? Anyone? I'm asking about this particular point. What color do you think this point should be? Is there a natural way to assign colors to the rest of the points? If I know that this point is yellow, this point is brown, and this point is green. So how would you assign color to this point? What is the most natural way you can think of? Green, good. But why? What made you say green? Nitin. Nearest one is green. So correct. Right. So we want to, among these 3 guys, right? So yellow, brown, and green, I will simply think, I will find which one is closest and look at its color and then assign that color to this guy. Right. So let me do that. Right. So if I do that to this data set, it's going to look like this. Right. So this was yellow. This guy became yellow because he was close to this guy than anybody else. These 3 guys are brown. These 3 guys are brown. These 3 guys are blue. Oh, I think there is one more stop going on. Anyway, so these 3. So this is what we'll call as a cluster step. So we start with some initial yellow, green, and brown, and then give color to rest of the guys. Now the point is, the way that you started earlier might or might not be correct, right? So in this case, though there were 3 clusters, I simply took these 3 colors from only 2 clusters. I did not use anybody from the third cluster, and that's how we kind of see this not so nice way of getting clustered, right? So, but a priori, before you start the algorithm, you don't know which are these three clusters to take one from each cluster. If you know that, then the problem itself is already solved, right? So I can only take it at random and do this cluster step. Now, what k-means algorithm says is that now don't stop here, go ahead further and do the same thing again, right? So now the next step, again choose a pivot, but now do the pivot choosing as picking the average or the mean guy from each of these individual clusters that you have generated so far. From the yellow guy, pick the one guy who's the average point of this yellow guys. From the brown guys, pick the average point. From the green guys, pick the average point, right? So it means pick some points like this, right? So these points, I mean, there are multiple ways to do this. These points might be one of the points that you already have, or maybe some point that was not there originally in your data set also. That could also be, I mean, because if you take the average, it might end up being here, which is not there in your original data point, which is also okay, right? So it's just, the algorithm does not differentiate between these two. In this case, what I have done is I have taken the point which is kind of closest to most point in the brown set, the point which is kind of closest to most point in the green set, and point which is closest to most point in the yellow set. And now what I'll do is I will start again clustering based on these new pivots, right? So I went from this set of pivots, did the cluster, took the mean, and I came to this pivot, and I will do again a clustering now. And now you will get a nicer cluster. Well, of course, you don't know if you have to stop here or not. You can again try to do this once more. Now, because we have a nice clustering already, if I take the pivots as the average of each of these clusters, you are going to get one of these yellow guys, one of these green guys, and one of these nice brown guys as pivots. And if you do the cluster again, it won't change anymore, right? So basically, you can declare that if it does not change at some point, I have finished my cluster. Right? So, and this algorithm is what we will call as the k-means algorithm. Well, why is it called k-means? It's called k-means because k stands for the number of clusters, right? So in this case, there are 3 clusters that I have chosen. So, which means I started with 3 pivots, and hence that 3 is the k here. And why is it called means? It's called means simply because every time I am, after doing a clustering, to get the pivots, I am taking the mean of the data points and choosing them as my pivots, right? So, and that's why it's called as k-means algorithm. Okay, so any questions about the algorithm before I go ahead and describe further? Okay, I think the algorithm is fairly simple and clear. So this step are so 2 very good questions. So the first question is about when does it stop, and the second question is about how did we start, right? So both are important questions. So the first question is so this step are going on until we did not get nice cluster. Well, yes, so you are correct, but how do we know whether the cluster is nice or not? The way to say that is, if I start with some clustering, now if I do this step again and I get new clustering, and if that new clustering is same as my old clustering, if it does not change, then I stop, right? So the hope is that when it stops, you end up with good clusters. So that is how you end the algorithm. The other question was about how do you start? So how did you pick these 3 guys? Well, in this particular example, I chose this as random, right? So, and there are ways, I mean, this is a very good question. So there are some nice ways to pick this first 3 guys in a reasonably decent way. But you can start with random ones also. There is nothing wrong in choosing with random. I mean, it will still work reasonably well, the algorithm. Okay, so any other questions before I move on and talk more about this algorithm? Okay, great. So let me move on. So now here is a data set, right? So how many clusters do you think are there in this data set? Just type your answer. How many clusters do you think is in this data set? Anyone? 2. Okay. 1. Yeah. Good. So people seem to say 2, and it's natural, right? So this is, it looks, oh, somebody said 4. Okay. So yeah. So this is another very interesting point about unsupervised learning, right? So there is no correct answer, right? So, well, 2 people seem to say 4. I don't know what is the 4 that they are thinking about. Maybe you're thinking this is 1, this is 1, this is 1, and this piece is 1, maybe, right? I don't know. So maybe that is, yeah. So that's what they're thinking. When people who are saying 2 are probably thinking these guys are all in one cluster, these guys are all in one cluster, right? So the you see the fundamental issue, right? So this brings a very fundamental issue about this unsupervised learning. There is no ground truth answer. You may think it is 2, you may think it is 4. There is no correct answer or wrong answer here. But for the moment, let's say for this question, we will think of this example, we will think it is 2 clusters. And now, if you run k-means on this, right? So if you run k-means algorithm on this with 2 clusters, which is a simpler example, can you think of what these 2 clusters will be? How would k-means divide these data points into 2 clusters? In other words, if we did whatever we described just before, do you think people who said 2 clusters, do you think k-means would put these guys in one cluster and these guys in one cluster? Do you think that will happen? Yes or no? Okay. Okay. Yes or no? I don't know if this yes for first this question or the previous question. So if you had given the answer to this question, can you say yes or no again? The question is, if you run k-means with 2 clusters on this data set, would you recover this as one cluster and this as another cluster? Yeah. So what fraction of people are saying yes? People are saying yes. Okay. 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 Few more answers. Any other answers? Anybody who thinks no? Interesting. Okay. People are maybe still thinking. I mean, the kernel trick, no kernel trick at this point. So let's simply think of this as 2-dimensional data, and I'm just running k-means on this. Will it still find these nice like moon type regions is the question. If the answer is yes, then you don't need any other tricks, right? So it turns out if you run k-means, its answer is going to be like this, right? So no, it's not SVM, right? So SVM is a supervised learning problem. We are talking about unsupervised learning. So if you run k-means on this data set, it will most probably will give you something like this, right? So it will say these are the guys who are in one cluster, these are the guys who are in one cluster. And I'm sure anybody who said this data set has 2 clusters was not thinking of this way of separation, right? So why does this happen? Well, it happens because this set of points is kind of closer to these points than these points, right? So there is no way k-means, because it's only looking at distances, there is no way k-means can say that this guy and these guys are in the same cluster, but then these guys are not, right? So that will never happen, right? So if you take 2 points in one cluster, then everybody in that line is going to somehow be on the same cluster. So what is somebody raises a point, based X graph, it's splitting. Well, yes, it is basically trying to. Yeah, it's basically the only thing that k-means can do is it can get some kind of lines, right? So it can only draw lines between the spaces. So in this case, it was only 2 clusters, so it will just draw one line. Whereas in the previous case, it would have drawn 3 lines like this, one line like this, and one line like this, one line like this, right? So it would have kind of drawn these 3 lines, and everybody on one partition these 3 lines would kind of divide your whole space into 3 partitions, and every partition will be one cluster, right? So that is the problem with k-means. So it can only draw nice lines and partitions that come from these lines. But then there are no, I mean, even if I draw 3 lines, I cannot kind of divide this properly, right? So that is the issue. So this is one major issue with k-means. It does not work for all nice data, all intuitive clusters. The other problem is, well, the first one question which was asked by one of the participants is, how do I initialize this, right? So did I take it at random? Is there a better way to do initialization? That's a very important question while running k-means. And the second question is, well, I said that I will stop the algorithm when the clusters don't change, right? So you have some cluster, you take the pivot by taking the means and then redo the cluster instead. If the clusters don't change, then you stop the algorithm and declare that, well, these are the answer. This is the answer. But what if the clusters keep changing in every round, right? So let's say there were 2 different clusters and it kind of kept jumping from one cluster, one way of clustering to another way of clustering, right? So then we will never stop the algorithm. So there is an issue of convergence that one needs to be careful about. Does the algorithm converge and stop at the cluster? This is an easier question to answer. So the algorithm is guaranteed to stop at some point. It might take a long time, but it is guaranteed to stop at some point, right? So this problem you don't have to worry about whether the algorithm will stop or not. So initialization, again, there are some heuristics to do good initialization, but that is probably beyond the scope of this talk. So I'm going to say that, leave it at that, saying that there are nice ways to do this initialization, and a lot of research has been done on this algorithm. We won't really get into that now because that is not the crux of the algorithm. Okay. The bigger problem, though, is that even though however well you initialize, you will never get this as one cluster and this as one other cluster, right? So because k-means can only draw lines, no matter what you initialize, it will draw a line. Maybe it will put a line like this, maybe it will put a line like this. It can put different lines, but it will never kind of divide this moon from this moon. Right? So for that, what typically people do is what is called as a graph-based clustering. What it kind of does is that somehow you, so without going to again too much detail, so somehow you kind of think of these nodes as some entries. I mean, if you know graphs with nodes and edges, for people who know graphs, you basically what it kind of thinks is you want to somehow think of each of these as nodes of a graph, and well, maybe let me put it this way: you somehow want to divide this into 2 partitions, let's say, such that the sum of what we call a similarity between pairs of points in different clusters is minimized, right? So what do I mean by that? I mean that, so let's say if this is how I kind of look at the partitions, right? So now what I want the sum of similarity between pairs of points in different clusters is minimized. If somehow I know that the similarity of people here to similarity of people here is larger than similarity of people here to themselves. If I can somehow come up with a similarity function like that, then I don't really need, I mean, then I won't really then I won't output this partition, whereas I will output the required partition, right? So, so what, I mean, maybe what I'll do is, in interest of time, so I'm going to say that, so the algorithm that tries to do this is what is called as a spectral clustering algorithm, for which the advantage is that you will be able to get answers where these two become 2 different clusters. And the algorithm itself works on somehow coming up with good similarities. And to come up with good similarities, you do what is called as a graph theoretic analysis of this data points. Let's not really well deep into that, but because it will again get us into more mathematical things, which I want to avoid in the introductory talk. So basically, if you do that algorithm, this is what the output is, which is what people who said 2 clusters initially were actually telling. Yeah. So so this is one other way of doing unsupervised learning. So so here is a question for all of you. So can you think of a real world example where unsupervised learning might be useful? Where you don't have supervision but still want to learn some clusters. Any real world example that you can think of? Right, so we are seeing so many algorithms, but then there should be some application there. Otherwise, why are we caring about these algorithms? Can you think of any useful applications? So I'll give you one example. Maybe you can come up with more examples. So let's say you have a MP3. You have a lot of MP3s, and you somehow want to extract. So the MP3s of songs, let's say Bollywood songs, right? Or some Hindustani concert or something like that. So you somehow want to extract out the vocal part of the MP3 from the instrumental part of it, right? So in a typical Bollywood song, somebody is going to sing and then instruments are going to be played in parallel, right? So I mean, it's not like somebody will sing and then the instruments will be there and so on, right? So it's kind of will be mixed together. Now, so given an MP3, nobody can come and tell you that, well, at this second it's only vocal, at this second it's instrumental and so on, because every second you might both have instrumental and vocal playing together. Now there is, in which case you cannot really come and supervise and tell you, okay, someone cannot tell which is the vocal part and which is the instrumental part. So in this case, if your goal is to kind of split the vocal from the MP3, what you could do is you can kind of come up with a unsupervised learning algorithm, where the MP3 itself will be converted into some bunch of features using some signal processing techniques. And now for these features, you will run a, let's say, a simple k-means algorithm with two clusters, where the hope is that in one cluster, all your vocals of each of your MP3 will fall in that cluster, and in the other cluster, all your instrumental part of every MP3 would fall in the second cluster, right? So basically, you can think of your MP3 as a superposition of two different waveforms. One is the vocal waveform, one is the MP3 waveform, and you want to automatically split this. This is one example. Can you think of a different example? Anybody? Where let me give you a hint. Think of an example where your smartphone is automatically doing some unsupervised learning. Can you think of one example in your smartphone where automatic unsupervised learning is happening? Anyone? Recommendation system. So recommendation system is typically a supervised learning problem because I mean, to predict, let's say I'm going to Netflix and then I'm being shown, hey, these are the movies you might like. How is it doing it? It is taking some features of me and trying to predict which movies I will like. And the way it will do it is, it will have people who have similar features like me would have already chosen some movies to watch. Now, that is the training data, right? Where the supervision is which are the movies did they watch, or for a given movie did they watch or not. And now using that supervised data, we can try to predict new movies for them. So it's typically a supervised learning problem, not an unsupervised, but a good observation. So are there any unsupervised learning problems on your smartphones that you can think of? In terms of, let's say, your photos, right? So that's another hint. So people with most high-end smartphones, I'm sure most of you have some kind of a smartphone over there. So Is there some unsupervised learning that's happening in your smartphone for your photographs? Anyone? Segregation of photos into what? That's a good point. As per places, excellent, right? So as per places, so your smartphone might automatically tell you that, hey, these are the places, outdoor places where you visited. This is your home, and so on. And in each of these cases, it is not really asking you to say whether this was outdoor or this was indoor or whatever it is. It is automatically doing that, right? So it may not tell you that. I mean, so the important thing to remember is that it might tell you that these places, these photos look similar, and this set of photos look similar, but it will not be able to kind of give you a name, right? So these are outdoor photos, these are indoor photos, because it would not know the names of these clusters. It can only give you clusters, and then you might want to give it your own names, possibly. Google Photos arranging based on places, foods, exactly, and even faces, right? So, I think some of the iPhones have this feature. I'm sure Androids also have it, where it automatically says, "Hey, these photos look like photos of the same person." Selfies, right? So it automatically figures out. Well, selfie is much more simpler, I think, right? So because it knows that you have used the rear camera, probably, but then more important thing is that it will tell you that, hey, these are the photos of this particular person, and these are the photos of this particular person. Now give me a name for this person, right? So it will ask you for that. It wouldn't know the name. It will only know that all these photos will look like the same person. Now if you give me a name, then I will name this cluster, right? So that's also typically an unsupervised learning problem. Very good. Yeah, good. Yeah, so these are all unsupervised learning problems in real life where all these kind of algorithms are constantly being used, and are more sophisticated algorithms, which we may have time later in some other. I hope somebody else will cover more advanced stuff later on. But yeah, so this is just to give you some kind of a sense of what unsupervised learning is. Okay, so in the next, let's say 20-25 minutes, what I want to do is also introduce you to another fascinating area of machine learning, slightly advanced, but very intuitive and interesting. It's what is called as online learning, right? So far, what we have seen is the following, right? So in all the problems that we have seen so far, there is some historical data, and you kind of learn this historical data, either a line or some function that maps input to output, or a generative model, whatever it is. We saw a lot of things. We are again talking about supervised learning now, not unsupervised. For the moment, we are switched back to supervised. But the main property or the main observation is that a lot of historical data was available, and we trained the algorithm on this data and then used the model that we got to make testing on unseen data. This is how our algorithm proceeded. Now, in a lot of cases, this may not be possible, right? So where you don't have a lot of historical data given to you on one shot, but where you will have to do your learning in an online or a dynamic fashion. Right? So this way of doing supervised learning is typically called as an online, right? So here is a simple problem to motivate this. Let's say you want to make some money, right? So, and the way you want to make some money is by investing in a particular stock, right? So I'm going to ask you some questions. So let's see how people answer. So let's say you want to invest in some stocks, in a single stock, and the hope is that you want to make as much money as possible. Now you have absolutely no idea about stock markets, how they work, and so on, right? So you don't know anything about stock markets. So naturally, what you go is you go and ask your friends, and let's say you have 100 friends. Here I have put them as n friends. Let's say for the moment you have n is 100. You have 100 friends. Let's say all the people in this participants in this group are your friends, right? And every day in the morning, you have to decide whether you want to invest in the stock or you don't want to invest, right? So you make that decision by asking your friends and somehow using their advice and make a decision. Now, the point is, only at the end of the day, you get to know whether your decision was correct or wrong. What do I mean by that? Right. Well, let's say you decided to invest in a stock. End of the day, if the stock market goes down for that stock, then it's a bad decision. On the other hand, let's say you did not want to invest in the stock at the beginning, but then at the end of the day, if the stock market actually went up, then that's also a missed opportunity for making money. That's also considered a mistake, right? The only time when it is not a mistake is when you invest in a stock and stock market goes up, where you make money. Or if you don't invest in a stock, but the stock market goes down, where you saved yourself from losing money. Those are the good decisions. Now, every day morning, somebody tells you, all 100 friends tell you whether to invest or not invest. And you somehow want to aggregate their advice to make a decision. Now, at the end of the day, it revealed whether the stock market actually went up or went down. And now, the next day, again, next day morning, all your 100 friends tell you whether to invest or not invest. And again, you make a decision. At the end of the day, you see whether your decision was right or wrong. And this keeps going on. Now, here's the thing, right? So, there is one stock market guru in this participant list who know exactly if the market is going to go up or go down, right? So, he knows, he's a guru, he knows exactly if it will go up or go down, and he will also tell you his answer. But unfortunately, out of your 100 friends, you don't know who this guy is. Okay? So there is one amazing guy who is always correct, but you don't know who this guy is. If you know who this guy is, then you will never make a mistake. You will simply follow his advice. If he says invest, you'll invest. If he says don't invest, you won't invest. And you'll always be right. But you don't know who this guy is. Now, I want to come up with an algorithm which will somehow make as less number of mistakes as possible over time. Because every mistake is a opportunity, is a lost money or an opportunity to gain money lost. Right? So you don't want to do that. Right? So you want to make as much money as possible and lose as less money as possible. So what algorithm will you use if 100 people are telling you either to invest or not invest every day? How would you go about doing this? And you know that one of these guys is a guru who will always get it right. Any thoughts? So let me ask so can we just observe and make data sets like which one is the guru? Good point. So you're right. So somehow we need to do that. But the point is you have to make a decision on every single day. You cannot simply observe and say I won't invest. Every single day you have to make every single day you have to make a decision whether to invest or not invest, right? Of course, you can keep observing what is happening. You have to, but then you will be counted for your mistakes on every day, right? So how would you go about doing this? So let me kind of guide you into thinking in a particular direction. There will be two types of data, yes or no. Yes, that's all. There are only two types of data. Each of the 100 people will say either yes or no, and you have to make a decision whether yes or no. How would you make a decision? Let's ask what is your decision on the first day, right? So you have no history data, nothing, right? First day you need to make a decision. 100 people are giving you advice. What would you do? We'll take an average on the first day. What do you mean average? You have to make a decision yes or no. Yeah, so what does average mean? Average is not an yes or no. No, number of them saying no and number of them saying yes. Okay, so you take the average. The average will be some number. And now what do you do? How do you decide to say yes or no? So let's say 70 people said yes, 30 people said no. Your average is going to be what? 50. We'll go with the maximum. Good, right? So the first day you are going to go with the maximum, as Kajol says. Hope I'm saying your name right. So let's say 70 people said yes, 30 people said no. and you go with the maximum. Now, it could be 50-50 also, right? So that is also fine. We'll come to 50-50 next. For the moment, let's say 70-30. Let's say 70-30. If it is 50-50, you can pick anybody, right? So there is no reason to say you should say yes or no. You can pick at random. But if it is 70-30, let's say I will go with 70. Now 70 people say invest, 30 people say don't invest. So I'm going to invest. Now, if I invest in the morning and in the evening, if the stock market goes down, right? So I made a mistake. Now, what does this mistake teach me? What does this mistake teach me? I made one mistake. The people who said no were right. That is one thing, right? So the people who said no were right. Not to go with the maximum, well, okay. So that is in this case we should not have gone. I mean, in this particular round we should not have gone with the maximum. Yes, but in general that seems to be a reasonable thing to start with. But Jasmita says the people who said no were correct, right? So, but now let's look at the special guy, right? The stock market guru. Where is he? In which group is he in? He is in the 30%. Good. So he is in the no group, right? So now, what will you do in the next round, the next day? Again, 100 people tell you advice. Whose advice will you consider now? So are you again going to go with the maximum, or are you going to do something else? Good. So you only have to consider those who said no, right? Because you know that the stock market guru is in the set of 30 people. The rest 70 people does not have him. So I don't have to care about the 70 people what they say. I only concentrate on these 30 people who made a mistake in the first round. Who were the minimum in the first round, and I take the maximum among these 30 people only. Instead of taking the maximum of all the 100 people, I'll only take the maximum of these 30 people, right? So let's say 20 people of these 30 said no, and 10 people said yes. Now I'm going to take the maximum, which means I will not invest. Now let's say that was a mistake. Now what do I learn in the next step? Where is the stock market guru? So I am only considering the minimum. Yeah, the guru, whenever is among the 10, right? So now I can reduce my space further down from 30 to 10, right? So I reduce from 10 to 30. I now reduce from 30 to 10. So when do I reduce? I reduce only when I make a mistake. If I don't make a mistake, I don't really know much, right? So but I mean, I know that the guru is in the maximum. But I can again choose to only go with the maximum. That is also possible. But more importantly, whenever I make a mistake, how much am I cutting the previous set of people whom I was taking the advice from? What fraction am I throwing away? At least. So initially it was 100. I threw away 70 people. More than half. Excellent. Why? Because we went with the maximum, and the maximum was a mistake, which means the whole of the maximum can go away, and the maximum will always be more than 50%. So you'll throw away every time we make a mistake. We are throwing away at least 50% of the remaining people that we are maintaining. Which means now the question is, if I start with 100 people at the beginning, right? So if I start with 100 people, what is the maximum number of mistakes I can make before I will stop making mistakes? The worst case, how many mistakes will I make? What is half? Half means what? 50? Is that what you're saying? So you will make mistakes on 50 days? Is that what you're saying? Think about it. You can make mistakes on 99 days? Again, think about it. Would that be the answer? So let's say, as somebody, I think Vivek was asked, 5? Good. Why 5? Why did you think of it as 5? So what is the worst case that can happen on the first day? 50 people said yes, 50 people said no. That is the worst case that can happen. So you are picking one at random. Let's say you make a mistake, which means you throw away 50 people, right? So you only retain remaining 50. And now in the 50, next day, 25 people, let's say yes, 25 people say no. You throw away 25, right? So exactly you will throw away half each time, which means from 100 you go to 50, from 50 you go to 25, from 25 maybe you will go to 12, from 12 to 6, 6 to 3, 3 to 1. And then that one guy will indeed be your stock market group, right? So which means every time I make a mistake, I cut the total set of people by half. And if I in general have n people, how many mistakes will I make? What is the relation between the number of mistakes and the number of people? What would that be? Can someone think of a mathematical relation? Okay, question and answers are 450. Okay. I may need 5 more minutes before we'll ask the question and answers. Oh, that's yeah. So I'm almost done. Yeah. So the answer to that question is how many mistakes will we make is logarithm of the number of experts. Why? So can someone quickly tell me why? Why it could be the logarithm? Log to the base 2. Well, maybe in the interest of time, I will tell you why that is the case. Because if you have, let's say, 2 power 5, 16 experts, the worst case is when you make the first mistake, it will become 8 experts, which is by 2. The second day mistake, it will become 4. Third mistake, it will become 2. Fourth mistake, it will become 1. And after 1, you will never make a mistake. So every time you are cutting it by 2, which means it will be like a logarithmic relation, right? So you will very quickly reach 1. And what is logarithm of 1024? Log base 2 of 1025. What is that? Anybody? What is log base 2 of 1024? Does anybody know the answer? Log base 2 of 1000. 10, right? So what does that mean? So that means even if you have 1024 friends to start with who are giving you advice, you won't go wrong more than 10 days, right? So which is much smaller than the number of experts. So very quickly you are getting the right answer. That's what it means, right? So this is an online learning problem where you can learn to do well over time by making use of the information that one expert is always right. So, but what is the most unreasonable assumption in this problem? Of course, the most unreasonable assumption is that there is a stock market guru who will always get it right. Well, it is unreasonable. Correct. It is unreasonable for 2 reasons. One is there may not be someone who can always predict it right, and even if there is someone like that, he's not going to tell you his advice, right? So that you will make money. So in any case, this is not a very reasonable thing to do. So then what can we do? So what we will do now is now we will assume the case, which is a slightly tougher case, but we will assume no expert will get it right. Right. So in this case, what can we do? In the interest of time, I'm not going to ask few questions, but then let me actually tell you what's happening in this case, and you can think about this more. So now what we will do is that so there is a chance that all your experts are not really experts, but then they are dumb people, right? So they'll always tell you the wrong answer, probably. Then there is no way you can use their advice to do something good. So then the way we will measure the performance of our algorithm is, so number of mistakes we make after, let's say, t days, minus the number of mistakes made by the best expert among us, among the 1024 people. If there is a true expert, true stock market guru who does not make any mistake, then this value will be 0. Then this will simply be the number of mistakes made by the algorithm, like how we had earlier. But then if there is no true guy who will always get it right, then we want to compare with their mistakes, right? So we want to be as close as to the best possible guy. If the best possible guy itself is making a lot of mistakes, then you cannot do much. But then you want to be as close as to be the best of your friends, right? So that's the best you can hope to get in this method. And the way to do that is what is called as a very, very famous algorithm in online. It's called as the hedge algorithm. And the algorithm is very, very simple. It simply maintains a weights for each expert, right? So instead of, so when an expert makes a mistake, in the previous case, we know that he no longer can be the stock market guru, then we'll throw him away, right? So you can think of that as reducing his weight to 0. On the other hand, in this case, this algorithm would say don't reduce his weight to 0, but then reduce his weight by a significant amount so that he still participates, right? So maybe later on he will get it all right. So you should still also have him under consideration. So you will somehow maintain weights for each of these experts based on how well they are doing. These weights will either increase or decrease, and you will maintain. Basically your decision will simply be based on the weighted majority in some sense, right? So if 100 people are saying, 70 people are saying yes, 30 people are saying no, you'll sum of the weights of these 70 people, sum of the weights of these 30 people, whichever weight is greater than 0.5, you will go with that decision. That's what is called as the weighted majority. Equivalently, it can be thought of as picking an expert probabilistically, but we will not go into that. Right. So this algorithm is known to give optimal regret. In some sense, it is the best possible algorithm. Of course, I have to tell you how to increase the weights and decrease the weights when a mistake or a correct answer is made. I won't have time to do that optimally. But then, I mean, I won't have time to do that mathematically. But then we will simply say that if you can balance the weights carefully, then you can get an optimal algorithm. Right. So to conclude, I want to finish by saying that all we have seen so far is just kind of a tip of the iceberg. There are several other popular settings in machine learning, like semi-supervised. We saw a bit of online learning. There's much more in online learning. There's what is called as a multi-armed bandits, what is called as reinforcement learning, transfer learning, and many more, which we did not have time to talk today. Yeah, so I mean, if you take a if you search for top 10 machine learning algorithms, you will see things like naive Bayes, which we saw today, support vector machines, which we saw today, k-means, which we saw today, and a couple of other things, neural networks, decision trees, nearest neighbors. These are things that we saw today. There are a couple which I could not cover today, but then there are many more algorithms and interesting methods in machine learning, many of which you will see hopefully in the next few days. So if you are a practitioner of machine learning, you are expected to, the go-to language these days is Python. And people also use R, MATLAB, and things like that still. For support vector machines, there are standardized libraries like libSVM, and of course, Google has its own TensorFlow for deep learning based methods and so on. Again, these probably will be introduced to you at some point. So if you want to know the mathematics of whatever we spoke today in much more detail, I think we should somehow understand 3 mathematical pillars of machine learning, which are linear algebra, probability, and optimization. So if you, in some sense, if you want to really get into the black box of machine learning, understand in detail what is happening in each of these, which we did not do today because it was an introductory lecture, you will have to understand these branches of mathematics very well. So I'm going to send this reference to all of you guys. So there are some nice reference books for machine learning, which are classic standard references, excellent references. And if you're a beginner, maybe you should start with something second one. And if you are slightly intermediate stage, you can go to the first one. And if you're an advanced guy, you can probably look at the fourth. Third one is also for beginners. Okay, so I have kind of finished. We can take questions depending on, any questions that feel free.
The participants can now raise questions. If you have any questions, you can use the chat box, please.
Questions, comments, suggestions? Did you like the session?
In case if you want to add on something or clarify something, you can do that.
Yeah. So why don't you guys So let me get some quick feedback for my own purposes. Can you again, I request all of you to kind of go to this, and so if it is A, you like poor. If it is B, it is reasonable. I mean, in terms of meeting your expectation, good. And so if you can type these, it would also give me some kind of feedback. You can do that while I can take some questions. Okay, so image processing and machine learning are linked. That's a good question. So image processing has been traditionally studied under the guise of signal processing. But yeah, so they are linked. So these days, most of image processing are dealt with machine learning. Earlier, the whole crux of image processing was in some sense trying to find good features from images, which is where the image processing community was trying to come up with a lot of nice ways to come up with features. Because images is just a bunch of pixels and you want to make sense of images in certain way. People are looking at a lot of features. Now these days, you probably will see talk about deep learning, where you will see that lot of image processing earlier methods have been replaced by automatically learning good features, which is what something called deep learning branch of machine learning does. I'm sure some talks will cover.